So welcome everyone to the September holiday revision event, including those who are online. So for today's class itself, how it will work out will be that the first half will be mainly going through content, and the second half will be going through the mock paper itself. Now, just to make sure that we're on the same page, the three topics that I'll be going through in the first half is mole concept, acid bases, and salts. All right, if I have time, I might do a little bit of QA, just the more important parts. As we go over into the second half and we cover the mock paper itself, you will also see a couple of topics that are not covered. Why? Because your Sec 3 end of year exam would usually contain more topics than just this three. But we identified these three as the most important ones that we need to go into detail. But you also see other parts like chemical bonding or even certain of the other chapters like redox, which is oxidation and reduction. Now, we understand only about half the number of schools will be testing on redox, so we'll still cover it if we have time, but that will not be a priority. Okay, so that will be the adjustment that we'll be making. Now, for me, I'm a little bit overkill, so I prepared an additional document specifically for mole concept because I think that that's a chapter whereby the more practice we have, the better we will be. All right, so for those who are physically here today, in my last row, can you help me with the stapling duties? All of you will be receiving an extra handout for mole concept. And for those who are online, I have already sent the link in the group chat so you can download the extra copy. But at the end of the day, what I need you to take away is the confidence when it comes to solving for your mole concept questions. Can? Okay, so maybe I'll settle the printing stack first. So I'll be back in 30 seconds. And thanks for printing. So, boys. So from the end up to the first thing like that, then there are the way the printer prints it, right? So that you read that, right? So let's see the last page will look like this was the exam. Right. So in this case, when you go to so your case, now anything Why? You recognize anybody? Okay, so yes. Self-service. Okay, sorry, let me continue. So I think it's important maybe for me to just share a little bit about myself. So my name is Darrell. In fact, I only teach chemistry and physics. The two branches that I'm currently teaching at is Kovan and Jurong East. Fun fact, I only teach Sec 4s. I've told this story multiple times, but the reason why I only teach Sec 4s is because that's when the desperation sets in. So I get highly motivated students that I enjoy working with. So for myself, I mainly teach at Jurong East on Wednesdays. So I actually have 2 Sec 4 classes later. And I also teach at Kovan on Thursdays. All right, so for the bunch of you, if you are here physically at Jurong East, likely you are from the west side lah, or you stay near here or study near here. So just as a very quick introduction to the space, this classroom actually, or this center actually only opened about 1 month ago. So it's very, very new. But I've been here for about 2 years already. It's just that we have been at another location. But we wanted somewhere more spacious. For me, I find it very important to have a high ceiling lah. So I feel like, wow, like a lot of space. So that's why we selected and chose this center that is relatively near to the MRT. Now, a bit more about myself. I've been teaching for 10 years now. I think that sort of gives my age away, but it has been ever since 2014 that I've taught students. I'll say across my teaching career, I have minimally taught over 1,000 students. I think this is less than what it says, but there's probably more lah, but I lost count lah. I don't find a point in counting. But my main point here is this. I can confidently brag that my students generally do very well at O levels. Majority of them, I'll say 60 to 70% per cohort score A1 or A2. But I think what's more important for you to understand is not just like, oh, so results, is it? Am I a magician, right? Can I just miraculously turn you into an A1, A2? The answer and why they do so well is that we work very consistently and there's a lot of work put into it. So let me just give you a sense of reference. So for my Sec 4 classes coming to class later, this week, right, their homework was 2 yearly papers. And we're going to go through 2 papers. And next week is another 2, and another 2 leading up to O-level. And before O-level, there will be 2 full mock exams as well, including practical. So it's just because of the consistency of the hard work and the time we put into understanding the subject and mastering it, that is the secret to doing well. So if you're thinking, wow, maybe after this, I want to sign up for tuition and stuff like that, my point to you is you need to know what you're signing up for. I guarantee you, you will be in striking distance between A1, A2 if you stay with me for at least a year. But every week, there's homework to be done. Holiday, there are extra work to be done. Sometimes I'll do extra classes, right? So if you feel like, okay, I'm ready to sign up for this because I'm serious about getting my A1, A2, then yes, this is for you. Otherwise, if you're like, hey, I come here, don't do homework, I just listen, I get A1, you're lying to yourself. Unlikely for you to get A1 if you don't put in the work yourself. So the secret is just consistency and hard work. There is nothing else. And that is why we are able to consistently generate good results. Okay? It's really about putting in the work. Now, one fun fact about myself is that I cannot drink milk. So every time I order bubble tea for my students, I'm very sad because all the milk drinks I cannot drink. Then I also don't like to drink sugar. So all the tea, the sweet one, I also don't drink. So half the time, right, I don't drink any of the bubble tea, even though I order for my students. There was one bubble tea that I drank that was highly intriguing. It was the Pi Pa Gao one from Koi, I think. Yeah, so I tried it. My students were very shocked about the taste as well. If you have a chance, you can go and try it yourself. So this is a little bit more about myself. Now, if this is your first time with OVERMUGGED, just like to introduce you very briefly to who we are. So we currently mainly focus on secondary as well as JC tuition. You guys, I think majority of you here are Sec 3s taking your EOY exam soon. So every year we generally guide and coach about 1,000 plus students across our 7 branches. You probably heard of us either from your friend, joining our Telegram channel on Instagram or TikTok. We are probably one of the biggest, if not the biggest tuition brands on social media. And I'll say what is important about this is just to help you understand that depending on where you stay in Singapore, there's probably a branch that's nearer to you. And we have very established tutors stationed at each branch. So if you come here for Chem Physics at Sec 4, it will largely be me. But if you go to other branches, there are also other good tutors that are there stationed to guide you through to your O-level. Now, results-wise, I think this is a bit of bragging, but we like to brag about this because it's just the amount of work that we put in reflecting in the results that we achieve. So 70% of our students actually score distinction at O-level and A-levels. Okay, to be very clear, it's not every time 70 lah. It's 65 to 70 lah. All right, I'll say that is being honest. It's roughly this range. And I'll say about 2 out of 3 will score A1, A2. And majority of our students actually do very well when they move on to A-levels due to the strong foundation they have built. But this is just a bit more. But I think I have already shared the secret to how we do well. It's really just consistent hard work. Now, especially for chemistry, I would say, one very important component is actually your practical. So while your school also conduct practical experiments and stuff like that, we find that it's insufficient because there's not enough guidance provided. So for our Sec 4s, they actually sit through a practical workshop, 3 weeks worth before their prelim, and 1 more practical workshop right before their O-levels itself. So we actually did titration as well as QA in our recent one, and that came out in a lot of their schools' practical itself. So we actually guide students not only for practical, but even for WAs, there's extra revisions free of charge. June holiday, we also do crash courses, and there's tons of cheat sheets and stuff. So after this lesson, right, remind me to give you a free copy of our periodic table. So we laminated it with all the trends behind and stuff like that. So I usually like to give out for the chemistry EOY revision. So remind me before I forget. For those online, unfortunately, I can't give it to you physically, but if you head down to our branches to collect, just ask for a copy. Usually our tutors and staff will just give it for free. So this is a little bit more about us, but I think what's more important for today is not so much about who we are and the results we have achieved, but are we able to use the next 3 hours as productively as we can to master the 3 topics as well as going through the mock paper. All right, and I think through this experience, you will understand the kind of growth you will get, all right, as you go through the lessons itself. Now, the first one that we'll be starting with will be mole concept. So I'm going to immediately switch gears to starting with the content and the teaching already. All right, so let's head over to the notes itself. I think majority of you here will have the physical copy with you. For those who are online, you can also download this as well. So the very first page that I'll be starting at will be this page over here. All All right, so even for the online students, I want you to flip alongside me to this page itself. Ken, ready? All right, so let's begin. So the first chapter that we're covering is mole concept. Now, something you will see me being very consistent with is that I strongly believe for chemistry, the moment you start memorizing, you are screwed. Same for physics, actually. But here's the thing. If your teacher has been saying, oh, memorize this, memorize that, I think it just shows for a lack of teaching, that they are not helping you understand the concepts more deeply. So you'll rarely find me saying, memorize this. Instead, I'll help you understand it, even if it spends more time on my end to explain it to you. So let me illustrate what I mean over here, starting with the very first definition, which is relative atomic mass. You can also look at relative molecular mass as they are very similar. There are two words or two parts to this definition that I need you to understand. Now, when we say relative atomic mass, this is when we head over to the periodic table and you take a look. You see this number over here, this 24. This 24 is referring to your relative atomic mass. But the main question here is this 24. What is the units for this 24? Is it 24 grams, milligrams, microgram? What does 24 mean? If you come to realize, right, the 24 actually have no units. Now, why is that important for you to understand? It's because when we use the word relative, relative is just in comparison to. And who are we comparing this mass to? We are comparing to the most commonly available element on Earth, which is carbon. Let me elaborate. So carbon, if you check the periodic table, the mass is 12. Why is it 12? Because it contains 6 protons and 6 neutrons. So we say a carbon has a mass of 12. Now, if carbon has a mass of 12, what is 1 unit of mass? We simply take a carbon 12 and divide it by 12. So when we say magnesium's mass is 24, it means that magnesium is twice as heavy as a carbon 12. Because magnesium is 24, carbon is 12. So what am I driving at? I want you all to understand the word relative. Relative means in comparison to. Now, let me give you a very simple analogy. Let's say for your upcoming Sec 3 end of year exam, you score A2. Do you do well or do you not do well? Most of you will say, wow, not bad, right? I did well. But what if the entire cohort all scored A1 and you're the only one that scored A2, right? It means in that context, you didn't do well. But what if you're the only one that scored A2 while everybody else failed? You'll be a chem god in the school already. So what am I driving at here? You need to understand the term relative. Relative means in comparison to. So all of the mass that you see in the periodic table, 24, 40, 88, this is all in comparison to who? To carbon 12. And if carbon 12 has a mass of 12, we consider 1 unit of mass, 1 over 12, the mass of carbon 12 atom. So the word relative means I'm comparing to carbon 12. Hence the term relative atomic mass. Can? So if you look at the definition, I hope you are not too bewildered. What is this talking about? You're just saying I'm comparing my mass with the base unit of comparison, which is carbon. Okay, that's the term relative. There's also another one I highlighted in yellow over here. This is the word average mass. I need you to understand that whatever you see in the periodic table, 24, or maybe more accurately, 35.5. This 35.5 here, it is an average because isotopes exist. There's chlorine 35, there's chlorine 37. Is when I find what's the average mass based on its percentage abundance that I get 35.5. You get what I mean, right? So, for example, one of my favorite analogies is this. My fiance's parents love to play Pokemon Go. When they go out to catch a Pokemon, right, sometimes you catch the normal version, sometimes you catch the rare version with better stats. So chlorine operates in the same way. Most of the time, if you see a chlorine, it's chlorine 35. But in the rare occasion, 25% of the time, you see chlorine 37. So do we say chlorine mass is 35 or 37? We cannot claim either, right? But we find the average. So when you find the average mass is 35.5. So when we use the term relative atomic mass, we are also accounting for the fact that isotopes exist. Hence, the definition in full is average mass of an atom of an element as compared to carbon 12. And this is the full definition. Now, is there still an element of you having to memorize this? I'll say yes. All right. But what's more important here is if you inbuild a bit of understanding, this part is easier to memorize. So never ever purely memorize anything in Chem. You need to build some understanding first, so it's easier for you to recall it when it's needed. Okay, so that's all for the first part. I'm not going to repeat again for molecular mass because it's almost the same thing. You just change the word here, atom of an element, to molecule of a substance. That's all. Next, let's immediately move on to the different formulas you see over here. Honestly, at first glance, if I'm a student, this is quite intimidating, right? Because there's a lot going on over here. There feels like there's a lot of formulas to know. But as per any science concepts, right? Formulas itself is just there to help you get to your answer. It doesn't mean you rely on the formula 100% by memorizing it. What does this mean to us? When we are solving a mole concept question, purely memorizing formula is insufficient. You need to actually understand how to solve it in what I call your 4 steps. Only after you have done that correctly, then you'll be able to apply the formula to solve the question. It's free sitting. I think there's one seat over here, so you can take a seat. Okay, so I'm not going to obsess over the formula. You can feel free to refer back to this list later on, but I'll say the priority is making sure that we understand how to utilize them. So I'm going to go through different question types bit by bit, and I want you all to focus, starting with calculating the percentage by mass of an element in a compound. Now, this one is actually fairly simple. Why do I say so? In a carbon calcium carbonate compound, which is CaCO3, all you need to do here is to find out of the 100 mR of calcium carbonate, what amount of it was made of calcium, made of carbon, and made of oxygen. Obviously, if I add up this 3%, what must it give me? 100%. No? So this is as straightforward as percentage by mass. Meaning in a compound, each element, what percentage is it consisting of? Can this be said as a question? 100%. All right, but I'll say this is probably one of the simpler concepts that you're seeing today. All good? Do you need the... Okay, let me pass it to you. In my voice, are you all answering? Yes? Okay. I might need to print extra because it looks like the turnout is a full house. I think I printed 22 copies. But can we start distributing first? Then anybody that don't have, don't worry, I'll print it for you right away. For those who are online, you will need to download this, okay? In the chat itself. Sorry, I see that there are questions. Can I? Yes. So keep helping me repost the link for anybody that joined late. All right, but don't worry, we'll continue to push on. Okay, now, I had a very deep discussion whether or not I wanted to cover this page in detail. So wait first, don't panic. A lot of stuff, right? Now, the good news is this. In the link that I have sent in the chat over here, it contains the full answer for this portion. So here's my take on it. Because I did a session last Saturday, I realized I didn't have enough time because I went through this entire segment in detail. I find that there's a lot more value in me helping you to solve questions instead. So what I'm going to do is this. Even for those who are here physically, later on, I'll print this out for you. Okay? But here's the thing, for those who are online, I'll need you to go and download this so that all the answers that you see over here will be relevant. What I'm going to do is I'm going to stay on this page for just the next... Okay, let me zoom in a bit. For the next 2 minutes, for those who want to copy this, to copy. At the same time, if you don't feel like copying, you can take a photo or I can print this out for you later. So there's very little stress. Yes, I'll print because I'm not enough copies later. Are we good? Ken? But I'll stay on here for 2 minutes for those who want to copy because some of you like to write it down right away. Okay, if not, I'll print out for you and stuff. It's not that this page is not important, but I'm prioritizing something that I feel is more important. Okay, Ken? Now, for those who are physically here, who don't have the extra handout today? One. Only one? Okay, I'll go and print 2 to 3 extra copies after this, but you need to give me a while. All right, so we're going to take the next 2 minutes for y'all to see this clearly. Let me see. I need to print that. Can I connect it? Okay, sorry, for those who are here physically and copying, I detached my laptop a bit first so I can go and print, then I'll plug it back in. Okay? So you'll give me a minute. But I need to go and print first so that it doesn't disrupt the rest of it. For those who are online, you should still be able to see this, no problem. But I will resume at about 1:58. I'll toggle to my other screen first so I can send in the printing. Sorry for the slight disturbance, yeah? Okay, for the rest, I'll stay on this page for now. Okay, sorry, coming back. Oops. Okay, I'll stay on this page first for those who are still copying. Okay, let me hide the floating panel. I recognize that what you're copying might not fully make sense, but I think it's with the intention that when you take a look at it, when you have time, it should make more sense. True. Thank you. Okay, so for those of you who are almost done copying, finish up. Okay, I emphasize again, it's not because it's not important, but because I think there are more important stuff to cover. So I think the way you can treat this is think of this as maybe an extra practice with the answer key provided. But what I'm going to be focusing on more, right, is on how you approach and solve more concept questions. So I'm getting down to the very real bit, which is if you ever get a more concept question, how should you be thinking about it? How should you approach it? And that's why there's an extra handout for today, because I find it to be a lot more useful, especially at Sec 3 level, for you to understand these details. Okay, so as I mentioned, I need to be stressed out about the copying part because it's already available online, or I can always bring you a physical copy. So now that it's 2 o'clock, I'm going to have a wrap on the copying part. Don't worry, because you will get the answers. Instead, right, let me have you focus on what is truly important for more concept, which is how do we solve questions. All right. So now with the extra handout that you have received, or you will be downloading later on, as you can see in the chat group, Thanks for helping me post. I'm going to head over to the extra handout itself, which contains a lot more questions that we can do immediately. So let me focus on the step-by-step process of how it should work. Who doesn't have the handout? Maybe you can grab it over there now. So I think one of you don't have, right? Yeah. Okay. So you will have this in your handout, and I've kindly printed my annotations as well. So the handwriting is not very nice lah. But my main point is that you don't have to write as much. So I want you to listen up very clearly. So for any more concept question that you get, it will always be a case of putting it into a 4-step process to solve it. Now, you might feel like, I really need these 4 steps or not? My answer to you is absolutely yes. I can confidently tell you, if you ask any of my Sec 4s in my class, which topics, right, they are most confident in, more concept will be one of them. Why? Because they have all mastered the 4-step process that will allow them to solve comfortably 80% of questions. So after today, right, let's assume you walk away from class today completely dazed. If there's only one thing I need you to take away from today's class, is how to use the 4 steps correctly. Because if you can do this, more concept will never be a problem. Furthermore, more concept is usually tagged on to other topics. So you do acid bases, they can bring in more concept, right? You do other chapters, they can always tag some form of calculation. So there's no running away from more concept. So this one, I'm covering it at the start while you're still fresh. Let me run through how this process works using a relatively simple question. So for any more concept question, they will usually give you some numbers to work with. They usually ask you to find something, mass or volume or whatever. Now, the very first step for any more concept question is to write out the balance equation. There will be question types where they will give you the balance equation. If they do, you can skip step 1. However, if they do not give you the balance equation, you must write it out yourself. And when I say balance, it means you need to add the coefficient to make sure that the number of atoms on both sides matches. Question? Where's the extra copies? Then you just take from her, okay? So I printed extra, or maybe it's your copy. Okay, but anyway, sorry, let me refocus. That was quite amusing scenario. So after you have your balance equation, you can then start the question. Now, what is this chapter called? Stoichiometry, right? It's called mole concept. So no matter what you do, right, step 2, what do we have to do? You have to find mole. Using any of the equation given, you have to solve for mole. And in this question, since 48 grams of magnesium is given, what do we do in step 2? We calculate mole. And what do we do with mass? We simply take mass divided by mR to find the number of moles of magnesium. Clear? Step 1 equation. Step 2, based on what they give you in the question, you will find mole. Sometimes you need to turn volume into mole. Sometimes you need to turn concentration and volume into mole. It depends. But either way, you must find mole in step 2. Now, how does step 1 and step 2 come together? Step 1 and step 2 allows you to do step 3 correctly. In step 3, you are supposed to find what we call your mole ratio. Now, what is mole ratio? Mole ratio is based on your equation. Let me go a bit deeper over here. When we compare mole ratio, we are comparing the magnesium with the hydrogen. Why do we do that? In step 2, you have already solved for the number of moles of magnesium. But it's a question asking you for magnesium. It's not, right? What is it asking you for? They're asking you to find hydrogen gas. So what should we do? We should compare the mole ratio between what we have found, which is magnesium, with what we want to find, which is the hydrogen. And how do we get the mole ratio? How do we get 1:1? Is by looking at the equation. If you take a look over here for the equation, 1 mole of magnesium reacts with 2 moles of hydrochloric acid to form 1 mole of your magnesium chloride salt and 1 mole of hydrogen gas. My point is, without the balance equation, you cannot find the mole ratio. So that's why step 1 is essential. There's no way you do a mole concept question without an equation. That kind of, if you get it correct, you are just lucky. Okay, so equation allows you to determine the mole ratio. What will you compare? You compare what you have found in step 2 with what you are attempting to find in step 4. So for this particular question, we are comparing the mole ratio between magnesium and hydrogen. And since the mole ratio is 1:1, if I reacted 2 moles of magnesium, how many moles of hydrogen am I expecting to get? 2 as well, right? Because their mole ratio is the same. So 2 moles will produce 2 moles of hydrogen. And finally, in step 4, we are supposed to find the mass of hydrogen gas. Now, what's the formula to find mass again? Mole times mR, right? So we simply get, we have 2 moles of hydrogen times the mR of hydrogen to get 4 grams. I can change the question as well, right? Instead of finding the mass of hydrogen, what if I challenge you to find the volume of hydrogen? Right? 2 moles times 24 dm cubed. Why? Because 1 mole of any gas occupies 24 dm cubed. So the final answer, if they're asking for volume, could be 48 dm cubed as well. But what you will find consistency in is that for every single question that we are about to go through later on, you will find it will always fit into this same 4 steps. Clear? So at first glance, it might not yet be intuitive, but you need to get used to the 4 steps itself. If your school taught you something similar or is slightly different, it is the way you think about solving a question. It's not about the answer. I don't care about the answer. It's how you solve it. All right, so we're going to apply this situation to different question types. And from there, I hope you'll get better at mastering this. All right, so we'll move on to the next question and let's see if you're able to get this. First thing I need to do is to give you probably 30 seconds to a minute to read the question first before we'll go through it. All right, I have already given you the answers. All right, so hopefully there's not much for you to write, but a lot for you to remember and understand. You definitely cannot skip step 3. Okay, because if you skip step 3, your answer will not be accurate. You always need to compare mole ratio. Let me give you some background context to this question itself. This question was actually found in the 2018 O-level paper. So whatever you're seeing over here is what you're expected to be able to solve by the time you take your O-level. But instead of focusing so much on the question itself, I want you all to recall the 4 steps. Once again, if you can walk away from today's class knowing the 4 steps, is good. It means you have really grew a lot through this session itself. So let's run through. What is step 1? Can we all recall together? What do we write down? The balanced chemical equation. Now, what's the good news for us? It's provided, right? So there's no need for us to take any action for step 1. Next, step 2. What is this chapter called? Mole concept, right? So step 2, conform plus chop, we need to calculate mole. I'll say the more important question here is, how do we find mole? What information was provided to us from the question? Do you all see over there, it says 0.49 grams of sulfuric acid. We are given mass. From mass, how do we get mole? Mass divided by mR. Therefore, in step 2, what you see is we are taking the mass divided by the mR to find the exact number of moles of sulfuric acid. Can equation find mole? What is step 3? Step 3 is to determine the mole ratio. So for those of you in the chat asking me about step 3, listen up. How do you do step 3? First thing you need to determine is the mole ratio. Who are you comparing with, right? Which are the 2 that you should be selecting? You should select the one that you have already found in step 2 because I know how many H2SO4 there is. So I'll be comparing against H2SO4. Now, who do I compare it with? I'll compare it with what I want to find. If we go back to the question is asking us for the volume of sodium hydroxide. To solve the volume with the concentration provided, what I need is the number of mole of sodium hydroxide. So what should I be comparing my mole ratio with? I should compare what I found in sulfuric acid with what I want to find, which is the number of moles of sodium hydroxide. So what I put down is H2SO4 versus NaOH. Now, how do I know that the mole ratio is 1:2? Anybody can tell me, how do I know 1:2 exactly? We refer back to the equation, right? That's why step 1 is essential. If you take a closer look at the equation, 2 moles of NaOH reacts with 1 mole of H2SO4. So the mole ratio is 2 of this will react with 1 of this. So over here, H2SO4 is 1. I'll need twice as much sodium hydroxide. This means that if H2SO4 I use 0.005, I'll need twice as much alkaline, which is why I times 2 to get 0.01. This 0.01 is the number of moles of sodium hydroxide that reacted. But is the question asking me for number of moles of sodium hydroxide? No, right? Can we take a look at the question? What is it asking for? It's asking for the volume. Do you all still remember the equation for volume is with concentration is concentration equals to mole divided by volume. So how do we find volume? We have to take mole divided by concentration. Now, question number 1, do we have the number of mole of NaOH? Yes, right? How much is it? 0.01, right? Because we compared the mole ratio to get this. Do we have the concentration? Where is it? It's provided in the question, right? Over here, 0.20. So by taking mole, which is 0.01, divided by the concentration, which is 0.2, I'm able to solve for the volume. You get 0.05 dm cubed. But the answer here is in cm cubed. So you need to convert dm cubed to cm cubed to get the final answer, C. This is O-level standard already. And all you need to do in order to get this mark in O-level is to know your 4 steps well. What I acknowledge is not all of you will look at this and go like, sure, I completely get it by now. No, impossible. Why? Because you likely haven't clocked enough practices for this to be familiar. But you need to accept that this 4-step process is what you need to know by the time you take your Set 3 end of year. So today, why I've taken away some parts of the notes, right, and I told you all I'll just send you all the answer, is because I want to spend as much time going through more questions. So the more we do, right, the more you're familiar with this 4-step process itself. Later on, I'll portion out one question for you all to try. So you can see you can apply. Some of you will still be stuck, but you need to get these 4 steps underway. Okay? So any questions at this point before I move on? So even if it's a doubt or any clarification, please let me know. For those online and those here physically. Any questions for these 4 steps? Kenna, I'll continue first. You are always allowed to check with me when you have questions anytime, right? So during the break or after class as well. So over here, right, I purposely selected what I consider a slightly harder version. So normally your prelim questions you get for Sec 4 taking prelim will always be a little bit more challenging than what is expected at O-level. So over here, I've selected a question. Same thing, let me give you about a minute to read through and to browse through the steps. Then I'll run you through how to solve it using the exact same 4 steps again. Okay, so 1 minute to read first. So how do you find the mole ratio for Sarah, who is online, is by looking at the equation. Okay, so maybe I'll just scroll back to the previous question for Sarah. The rest, please read. You should have the copy with you. So the mole ratio that we're looking at over here is between H2SO4 and what we want to find, which is NaOH. If you go back to the equation, can you see the NaOH, the number in front is a 2, while for H2SO4, there's technically no number in front, which means it's a 1. That's how we determine that the mole ratio between H2SO4 and NaOH is 1:2. Then this 0.005 came from the calculation in the previous step so that you can find what you're looking for, which is the number of moles of sodium hydroxide. Okay, so how to compare mole ratio is based on the numbers you get from the equation. Okay, if not, I will take a look at question 28. So for question 28, same thing. It has to be the same 4 steps. Step 1, what is it? Balance equation. What's the good news here? Question provided that for us. Life is great. Okay, so step 1 done. Step 2, what are we supposed to do? What's this chapter called? Mole concept, right? Conform plus chop, need to find mole. So let's look at in the entire question here, what information was provided that will allow us to find mole. Can anybody tell me confidently what info should we be using here? I got 20 plus brains here. Confirm know the answer, right? So how to find mole? We use the Mass law, because the mass is provided. So you see over here, the question said we're going to be reacting with 0.239 grams of lead sulfide. So this is your lead sulfide. So how do we find more of lead sulfide? Sorry, this one I think is a minor typo. You should write PBS, right? Because we are finding the number of moles of lead sulfide. What do? We'll take mass divided by MR. MR is the molecular mass. You simply go and find lead. Lead in the periodic table is 207. Sulfur is 32. So when you add it up, it gives you 239. Okay, don't ask me how I memorized it. I've been teaching for 10 years. You check periodic table will do. No need to memorize. But the main point is that after you take mass divided by MR, you will get the number of moles of lead sulfide, 0.001. Slow down here, because step 3 is where it gets confusing, right? Step 3, we compare mole ratio. Now, what do we compare mole ratio with? What we have found, compare it to what we want to find. What have we found? PBS. The question is asking me for mass of hydrogen peroxide. So what should I compare it to? I should compare it to hydrogen peroxide. So if you go back to the equation, there's no number in front of PBS, so we say that this is 1. What is the coefficient in front of hydrogen peroxide? 4. So when I compare my mole ratio, what's my ratio? 1 PBS gives me 4 H2O2. So if I use 0.001 mole of PBS, I need to get 4 times as much H2O2. So what is the mass of hydrogen peroxide that we require to react? If you are using 0.004, I will just take mole times MR to find the mass of hydrogen peroxide required. Step 4 is always solving what the question is asking for, right? But you will probably need to use some formula over here. But recall at the start of the lesson what we said, it's not about the formula coming to save you. You need the formula for sure, right? You need to know mole equals to mass divided by MR. You need to know concentrations formula, but it's just part of the question. The bigger picture you need to get is the step-by-step how I get to my answer. The formula will come in step 2 and step 4. Clear? 4 steps, it will never change. 80% of questions will look like that. But the question, they will make it look a little different. Sometimes they will change things up. But it doesn't escape these 4 steps. Later, I'll show you, right? Even for percentage purity and percentage yield, it's the exact same thing. Which is why today you must learn this. Okay, if you walk out of class today without learning this, I have failed my job. Meaning I didn't teach you well. Okay, so far can follow? Questions? Okay, we keep going a bit. All right, so we push ourselves one step further. For this question itself, I did leave the annotation. It was a bit of a mistake on my end because what I want you guys to do is to try this question from scratch. Okay, so for those who are online as well, I think yours is the blank version, but those who are physically here, I printed with the annotation. But if you don't mind, or if you need a foolscap pad or anything, can I challenge you all to try this question from scratch? And I'm going to give you a solid 2 minutes to try it. Anybody that needs foolscap, just pass the foolscap pad around and take a piece of paper. Can? Anybody needs it? Can? So pass it around. Anybody that needs, just go and grab it. At the end of the class, I'll give you one copy as well. Okay, so for those who are here, go try. 2 minutes. Those who are online, I want you to try as well. There's only one thing here. I want you all to go and try to apply the 4 steps. Okay, I will guide you through this later. Okay, if you came with your friend or if you're online, I completely allow you all to discuss this. So go and figure out how to apply the 4 steps to solving mole concept. Okay, I'll erase away this. And this. Okay, I'll start at 222. Okay, another 30 seconds, then I'll start. Okay, let's try. So if you haven't finished, it's fine. I'm sorry, but I want to make sure we have the pacing in place. Otherwise, later on, we won't have enough time. But the core emphasis of getting you to try is so that you start getting comfortable applying your 4 steps. I need a bit of your participation here. All right, I don't like to call somebody out because you all might be a bit pricey, but you know the answer, you just shout out. Wrong, right? I'll just act as if I never hear. Okay, so don't need to pricey. Help me out. Step 1. What's step 1? Balance equation, right? So let's do it step by step. Step 1, I'm going to write that down. We will always form the balance equation. Did the question give us? Don't have. Need to write ourselves. But it's nothing we cannot do. Why? Because we should recognize magnesium is a metal, right? And hydrochloric acid, is acid. My question is, metal plus acid, what does it give us? Salt plus hydrogen gas. So let's attempt to form our balance equation together. If I'm wrong, you stop me. So Mg, I'll just write down metal. What is hydrochloric acid? HCl. I think most of you do know this. It forms salt plus hydrogen gas. So let's start with salt first. Mg with the Cl. MgCl. Wrong. Why wrong? Mg, what's the charge? 2 plus, right? Cl, what's the charge? Minus. Is it balanced? No, right? So which one do I need more of? Chlorine, right? I need 2 chlorine to 1 magnesium. 2 plus to minus, so I need 2 of that minus. So it should be MgCl, there's 2 of it. Next, what's the other product? Hydrogen, right? H. Why wrong? Hydrogen, I write hydrogen, right? H2. My question is, right, why do we write H2? Why not H? Is diatomic, right? Now, there's 2 things I want to teach you all here. This is my own observation. Whenever I have group tuition classes, right, and for the guys, right, when the guys go toilet, they just go by themselves. When the girls go toilet, must always go buddy system one. I do not know why that's the pattern. So that's how I want you all to remember diatomic molecule, right? Because it's always in pairs. But for me, there's always one version that I like to teach you all. How do you remember which are diatomic and which are not? So if we head over to the periodic table, let me show you all. I want to show you all this. Now, why is this very important? I always use this same story. Do you all know what are the 7 wonders of Earth? Actually, I don't really know. I only know one of them is the pyramid, okay, in Egypt. But my main point is I want you to remember when we say diatomic, I want you to remember 7 wonders. Which are the 7? Firstly, it starts at number 7, which is nitrogen. How many of them are there? 1, 2, 3, 4, 5, 6, 7. And you see the shape of it is also in the shape of a 7. So what am I trying to get you to remember here? Whenever you form balanced chemical equation, you form nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine. It will always come in a pair. It will be diatomic. How many of them are there? 7. But not really 7, because there's plus the 1 that got away. So what's the last one that should be diatomic? H2. So in total, when we are forming chemical equations, how many of them will be diatomic? 8 actually. 7 plus 1. Can? Because this one, right, the shape of a 7 with 7 of them, beginning at 7, you won't forget. But if you try to memorize this individually, you might get confused. All right, so my main point here is remember, whenever we write any of this 7 plus 1, it always comes in a pair. If you don't, your whole equation will be wrong. The rest of it will be wrong already. So getting your equation right is step 1. All right, and this is the one to look out for. So for those of you who are trying by yourself, I don't want to say that you did make this mistake. But I'm quite certain a couple of you, whether online or in person, might have made this error. So remember, hydrogen, it comes in a pair. All right, and in the future, any of this 7 plus 1 appear, remind yourself it's always diatomic. Now, I have formed my equation. Am I done? Why not? I thought, so you say step 1 is form equation, what? Why you all say not done? Form a balanced equation. So which part of this is not balanced? There is 2 Cl here, there's 2 hydrogen here. So what should we be writing here? It's 2 HCl. Okay, only then you have completed step 1. Next, step 2. Can you all remind me what is step 2? What is this chapter called? Mole concept. So step 2, conform plus chop, you need to calculate mole. No choice. So step 2, we're going to calculate mole. But I guess what is more important to me is what information was provided in the question to help me calculate mole. Do you all see over here when they are asking for blah, 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 we see 100 cm cube, 1 mole per dm cube. In case you haven't realized, 100 cm cube is just volume. This one over here is concentration. So this is referring to your hydrochloric acid, which means in step 2, you're calculating the number of mole of HCl. Now, how do we find mole? If concentration equals to mole divided by volume, how do we find mole? We take concentration times volume. All right, so we take concentration multiplied by volume. Let's add in the numbers. Concentration is 1.0. Volume is 100. You know my face like that means something wrong, man. But what's wrong? Sure, you tell me concentration times volume, I write down, you tell me I'm wrong. Why? Right, the units, right? So for those of you who didn't notice this, right? Zoom in a little. What's the unit for volume here? cm cube. What's the unit for concentration? dm cube. Are they the same? They are not. So what should you do? You don't go and change concentration. Very complex. You go and change your cm cube to dm cube. For those of you who are not very confident with this, just remember 1 cm cube is the equivalent of 1 ml. 1 dm cube is literally 1 liter. 500 ml is how much of a liter? 0.5 lah. You know, you buy 1.5 liter water, is 1,500 ml. So you can always use the ml and liter to convert if you're not confident. But my main point here is that 100 cm cube is how many dm cube? We need to divide by 1,000. Clear? This is another area that you'll make mistake. So every time I pause, it's not because I purposely trying to slow down. It's because I'm trying to catch areas where you guys will make the mistake. So I'm trying to get you to avoid making this because now you're aware. If I go back to the question, you will get 0.1 mole. Step 3 is where we consider it to be slightly more challenging as we are doing mole ratio. Now let's recall, mole ratio will be between 2 things. It will be between what I have found in step 2 with what I want to find in step 4. What have I already found? I have found HCl, right? What is the question asking me for? Is it magnesium? No, right? Actually, the question is not asking me for magnesium. What do they ask me to find? Maximum volume of hydrogen. So the mole ratio comparison here should be between what I have found in HCl with what I want to find, which is H2. And how do I know the mole ratio? Based on the equation, right? So that's when step 1 is linked to step 3. For HCl itself, what's the number? 2. Hydrogen, what's the number in front? 1. Which is why when we compare mole ratio, HCl, I'll write down, is 0.1. So how many moles of hydrogen will be produced? 0.05. And in the final step, step 4, what do? We solve what the question is asking us for, which is volume of H2. Volume of H2, volume means 1 mole is 24 dm cube. So over here, we'll take mole times 24 dm cube. And how many moles of hydrogen do we have? 0.05 times 24 dm cube. Your final answer, 1.2 dm cube. Answer is A. The 4 steps are eternal. There's no running away. All right, even you go like, wow, they are very hard, right? You still need to learn. But once you get it, you never have to memorize it again. This is not memorizing, right? It's quite logical. It's just that you need to spend some time to digest this. And I hope through today's class, I spent quite some time on this, but I know it will be worth it. Because your Sec 3 end of year exam confirm have more. And more will always be one of your weakest topics, I think, right? Across the many batches that are taught, it's always consistently the hardest. But it's because you guys have never properly learned these 4 steps. Are we good here? Okay, I'm going to put a pause to this 4 steps, not because it's not important, but because I need to move on to some of the remaining concepts that are equally as important in this chapter. So the next thing I'm going to bring your attention to is the concept of limiting and excess. Let me give you a bit of a backstory here. When we say limiting and excess, what I need you to understand is that whenever we react to chemicals, we cannot assume that we always add in the perfect amount and everything react with each other. There is likely a case of me adding too much of something or too little of something. Too much means excess. Too little means limiting. But I always find that there's value in terms of going through this analogy with you. So my dream car that I wish to buy one day is a Tesla. But freaking Elon Musk, his car's too expensive. I cannot afford, okay? But that's my dream car. But let's put it in a factory context. Currently, my manager at the factory takes stock. How many car bodies does he have? He got 4 car bodies. And when you go and count how many wheels does he have in stock, there's 12 wheels. My question to you is, how many cars can we form? I got 4 car body and 12 wheels. What's the maximum number of cars my factory can produce today? 1. 1, because the worker tired, right? Not 1, 3 or 4? 3, right? But I got 4 car bodies, why only get 3 cars? Because I only have 12 wheels, right? Each car will need 4 wheels, so I only have 3 sets. And I can only form 3 cars in total. In this exact context, which is excess? I got excess car bodies, which is limiting me from producing more cars. What is holding me back? The number of wheels. So the term excess and limiting is just talking in terms of your reactants, what you need for the chemical reaction. Which one I got too much, which one I got not enough. Does it mean the smaller number is always limiting? No, right? As you can see in this context, I got lesser car bodies than wheels. But what matters is the chemical reaction and the mole ratio itself. That will help you determine what is limiting and what is excess. Can follow? Yeah, I bring you another level. Upgrading. You go back up, right, and take a look at this statement over here. The other concept that is highly linked to excess and limiting is your mole concept for gas. Let me simplify this for you. When you're dealing with gases, it doesn't matter which gas you are. Your MR is irrelevant to me. Why? Because any gas, 1 mole is 24 dm cube. Mole and volume is directly proportional. Summary, what you need to learn here? Your mole ratio itself is your volume ratio. I repeat one more time. Your mole ratio is your volume ratio. Now, what do I mean? If you take a look at this equation over here, the mole ratio is 1, 3, 2. It is equal to your volume ratio, which means if I react 10 cm cube, it will react with 30 cm cube to produce 20 cm cube. 1, 3, 2. 100 can react with 300 to produce 200. 1 dm cube can react with 3 dm cube to produce 2 dm cube. Your mole ratio is your volume ratio. Clear? So this is the other part that I need you all to digest. Why is it so important? If I combine excess limiting with gas mole ratio, it combines together to form a very common question type. Good news, bad news, it was tested in last year's O-level. This exact question, whereby they combine these 2 concepts together. Prelim, they love to set. End of year exam, likely to set as well. Later on, you'll find it in a mock paper as well. I'll highlight it when it comes out. But let's use this chance to see how the question look like and how we are supposed to solve it. Okay, I'll just give you all 30 seconds to digest the question. I'll guide you through fully on how this works. If you are not prepared for this question type, it's unlikely you will be able to solve it in your EOY. Okay, which is why we need to get this right before I can move on. Okay, just read the question for me. Let me do my job to guide you through on how this works. Anybody have seen something of this question type before? Looks familiar? A bit, right? Okay, so I think if you have done sufficient practice of your school gave you, they should give you this question type, right? So this question type involves two concepts. Number one, remembering for gas, your mole ratio is your volume ratio. That is the prerequisite number one. Second one, right, I'll say what you want to look out for in the question. If you see the word, gas left or volume of gas remaining, that is signaling towards the fact that this question, there is excess and limiting. So when we combine these two concepts together, how would it be tested? So what I've done over here is I've copied out the exact equation so that I can see it more clearly. Can you all see that the mole ratio here is 4, 3, 2? Okay, so the ratio is 4, 3, 2. The question told me initially I had 40 cm cube of ammonia. I have 60 cm cube of oxygen. This is my starting material. It's the same as my factory, remember the car factory? This is how many car bodies and how many car wheels. Same idea. Do we expect all of them to fully react? We don't. Because the question, if they say gas left, meaning there will be excess and limiting. So we go back to the equation. 4, 3. If I react 40 cm cube of ammonia, how many cm cube of oxygen would I have reacted with? 4, 3. So 40 will react with 30. You get? It's just a ratio. 4 is to 3. 40 will react with 30. But what does that mean to us? It tells me that I'll use up all of my ammonia. But I had 60 to start, and I only used 30, which means I will have 30 cm cube of oxygen in excess, left over. I didn't react all of the oxygen. There is some that were unreacted. Now, the ratio is 4, 3, 2. So if I reacted 40, 30, 4, 3, 2, how much nitrogen gas should I produce? 4, 3, 2, 40 and 30 will give me 20 cm cube. So if the question is asking me, hey, what is the volume of gas left? I need to add what I have formed with what was unreacted in excess. So the 20 plus 30 would then give me the volume of gas remaining to be 50 cm cube. Is this easy? No, which is why I'm going through with you today. So what are a few things you need to understand from this question? Mole ratio is your volume ratio. Next, if the question has volume of gas left or volume of gas remaining, you need to identify which is in excess by how much. The total volume of gas remaining is what you produce and any leftover reactants. You add that up, it will give you the volume of gas remaining. Now, one very important question to ask. Sure, you say 4, 3, 2, right? Why do you ignore the 6 water? Isn't it part of the equation? Why did I not calculate the volume of water? Why? Gas, right? So you'll take a very close look over here. This is calculated at room temperature and pressure. What is water state symbol at room temperature? Liquid law, right? So is it a gas? No. So we don't add in the water, even though it is part of the equation. Can? Easy? Not really. But must you learn this? Definitely. Okay, so on my end, what I'm going to do is I'm going to go through this question again later on as we look at the question in the mock exam. So you will have another exposure to limiting and excess. But I hope at least for now, this is clear. Are we good? Okay, now what I'm going to do is I'm actually going to go back, right, to the notes. The one that you have in your revision kit. All right, I'm not going to go through this. This is, you can consider it to be extra practice. But I want to bring your attention to this next part for percentage purity and percentage yield. This time around, I will not give you time to copy. So you either take a photo, wait for the handout later, or you can screen capture it. Or for those who are online, you can already download this. So I'll just give you 30 seconds here. Once again, it's not that this part is not important, but I prefer to use an actual question to run you through. This one, you can fill in the blanks yourself since it's just fixed answers and numbers. So what I'm saying is don't worry, you already have the answer. Allow me to run you through how to think about percentage purity and percentage yield. That is the true value you'll be getting today. Okay, let me toggle to the question, if you don't mind. Sorry, but I want to move on because I need to make sure that the pacing that we're going with stays consistent. Okay, the next question that we'll be looking at is this question 34. So maybe we can all flip over to this question and let me have a deep discussion with you over here. Okay, this question itself, once again, where is it anchored at? It is actually an O-level question. It came out in 2014, which means this is the expectation. You need to be able to solve a question like that. The first thing as a student you want to identify is that this question is on percentage purity, right? So you need to identify, okay, this question is about percentage purity. But internally, this is what I need you to know. You must firstly recognize the formula for percentage purity, which is percentage purity is found by taking the mass of your pure substance over the mass of your sample. Your sample would definitely contain impurities. So when you do a simple fraction times 100%, you'll be able to find out of this impure sample, what percentage of it was actually the pure thingy that we are supposed to react. Okay, so percentage purity will always be lower than 100% as a result. Now, how do we solve percentage purity question? Surprise, surprise, you are still doing the same 4 steps. There's an additional one at the end, as you can see. I called it step 4.5, which is just to bring in the percentage purity formula at the end. But if you come to realize whatever we're doing here is no different from the mole concept framework we have studied earlier. So let's run through how this process works. For any percentage purity question, I need you to know that you'll be given 2 numbers. Confirm one. In the previous question, it was easy. Why? They only usually give you 1 number. You will find more from it. But for a percentage purity question, you'll get 2 numbers. And here's the confusion. Yes, sure, I understand. We need to form balance equation. No problem. But when I count mole, right, do I use this 23 or do I use this 4.49? Which one do I use to calculate mole? That would be your dilemma. And let me clarify, right, which one you should not use. The one that you should not be using is the mass of your impure sample. The question will provide you with this value. For this question, chalk is impure calcium carbonate. And they tell you that chalk itself has a mass of 23. This 23, you will reserve it and you will only strictly use it in the final step, in step 4.5. You do not touch or use this 23 in any other calculation. Not until the final step. If you do not do this, the whole question will be screwed because you're starting with the wrong value. So I repeat one more time. For any percentage purity question, the question will give you the mass of your impure mixture. Otherwise, how are you supposed to know what the impure is, right? Because impurity, the percentage is unknown. You can't calculate anything. So the question will give you, but you need to have the awareness not to use that. You only use it in the final step when you take it divided by the pure. Your job instead is to use this 4.9 to calculate until you are able to find the mass of your actual pure calcium carbonate. Only then you take the 18.7, which is calculated using your 4 steps, divided finally by the mass of your impure sample to calculate your percentage purity. I can go through with you step by step again for the 4 steps, but by now you know what I'm referring to. What is step 1? Equation. Step 2, we calculate mole. And this time around, we use the 4.49 to calculate the number of moles of CO2. Now, what am I trying to find? I'm trying to find the pure calcium carbonate. So I compare mole ratio, I find the mass, and only then I bring in the mass of my impure sample to calculate my percentage purity. Can? So is percentage purity question a new question type? Absolutely not, because you're still doing the same 4 steps, but with an additional formula in step 4.5. That is how you should be thinking about percentage purity questions. Can? The working is there already, right? So you don't feel confident, go back and revisit it. But other than percentage purity, there's one other one that's very similar, right? What is it called? Percentage yield. All right. So let's look at the sister of the question, which is percentage yield, and what is going on over here. Now, the context of it will still be the same. In this question, you will be provided with 2 values, 10 gram, 12 gram. The same dilemma appears. Which one do I reserve and use it only in the final step versus which one I should be using to calculate with my 4-step process? So over here for a percentage yield question, how do I want you to remember this? Okay, we are about midway through your March holiday. So let me give you a very simple analogy. March holiday, usually you go and plan, right? One day you want to spend how many hours revising or doing your holiday homework? Let's say, we say today I'll study for 4 hours. In reality, how many hours do you usually study? Confirm less than that. You don't tell me more than that. Usually impossible. So when we are looking at theoretically what you plan for versus your actual output, your actual is always going to be less than your theoretical. You all get what I mean? So the actual output is always lesser than what you predicted it to be. So how does this question work? The actual output itself will be provided by the question, because you wouldn't know on that day itself what is the output. So the actual yield, at least in this question context, we produced 12 grams of bromobutane. This is actually what came out of it. This is the actual amount. Your job is to use this 10 gram, go through the 4 steps to find out in theory, how much was I supposed to get? If I reacted 10 gram of butanol, 10 gram of butanol is equivalent to this number of mole. When I compare mole ratio, I was supposed to get 18.5 grams of bromobutane. But how much did I actually get? I only got 12. So what is my percentage yield? I take my actual output that the question told me, divided by what I calculate, which is the theoretical yield. And when I times 100%, I'll get my percentage yield itself. Percentage purity and percentage yield is similar, but not the same. We run through the thought process again. For percentage purity, which was the previous question type, which value do I reserve until the final step? We reserve the mass of your impure sample, right? I'll use my other value to do the calculation. For percentage yield question, which one do I reserve until the final step? Your actual yield. What you're supposed to calculate using the 4 steps is your theoretical yield. Because once you get this framing, you will never ever get confused again. If you can do your 4 steps, you remember this discussion that we had, these question types are all technically 3 marks, because you just need to calculate. The number will change, the equation will change, but the way to solve it will stay the same. That's the beauty of mole concept, which is once you master it, you never have to worry about it ever again. Clear? So I spent very long on mole concept, not because of what, but purely because of how important it is. All right, but at this point in time, I cannot really continue going on. Otherwise, I wouldn't have time for your remaining stuff. So I have to pause here for mole concept and wrap it up. So what is your main takeaway? We covered 3 things. Firstly, right, we drilled down on your 4-step framework. If today you walk out of the classroom and you cannot tell me the 4 steps, I'll cry already. What are the 4 steps? Let's recall one time. Step 1, balance equation. Step 2, calculate mole. Step 3, mole ratio. Step 4, you solve it. Sometimes there's a 4.5, right? If it's percentage purity or percentage yield. The second thing that we covered today after the 4 steps was limiting and excess, right? And the question type that you're likely to see is when there's the mole ratio for gas with the volume ratio to calculate limiting and excess. We'll see that question again later. The last bit we slightly addressed it is percentage yield and percentage purity. Generally, if you can do these few question types, most of your Sec 3 end of year exam questions shouldn't be a problem. Okay, but you need to clock the practice. That's why I printed extra questions in this handout with the answer key as well. So you can go and look through, go and try. The more you do, the better you're familiar with the 4 steps. Mole concept will be one of your strongest topics moving forward. Make it that case. All right. If not, without going on any further, I will go back to the notes once again because there's a few more annotations that I've included. But same thing as before, it's not that it's not important, but I want you to treat this as extra practice on your own. So once again, I'll encourage you to take a photo. All right, and those that are online do so as well, and slowly copying my annotations. Okay, I could have went through this bit by bit, but I found like going through the questions is more impactful. So for me, I'm just like changing things up a little for your own learning. Okay, so snap a good photo. If you took a photo, send it to your friend, no problem as well. I will move on to the other part with annotation. Then I'll move on already. Sorry, I need to move on to here. Okay, so once again, maybe you can take another photo here as well as the next part. Then I'll move on to acid bases. Okay, so treat all of this as your extra practice after today's class. You can always refer back because you do have the official answer. Okay, for those online, you can take out your phone to take a photo or even a screen capture works as well. But treat all of this filling in the blanks as extra practices. Remember what I went through in terms of the 4-step framework. Okay, one last photo before we wrap it up. Okay, so this is the final bit. Okay, Ken, so I think I'm wrapping up the first half. We spent a lot of time on more concept, but I think it's worth it. I really think it's worth it. But you all must take away your learnings today. Okay, if you revert back to whatever old way of doing it, you didn't learn, you didn't grow. So remember the 4 steps. You don't have to write step 1, 2, 3, 4. Don't need. These are our own internal lingo, but you need to express all of the steps accordingly. With that, I'm actually now going to move on to acid bases, followed by salts. After I'm done with that, I'll give you all a break, all right, before we go through the mock paper itself. So let's start with the next chapter, which is acid bases. The good news for me is this. I feel that you guys do know acid bases to a certain extent. But let me emphasize on the more important parts I need you to remember. Now, the first discussion here is the word strong versus weak acid. Now, in our syllabus, right, there's only 3 strong acids I need you to remember. It is HCl, HNO3, and H2SO4. Everything else is a weak acid. Next, when we say strong acid, I need you to know that the definition is that it fully dissociates, while for weak acid, it only partially dissociates. This is why you see a difference in the arrow used, because something that fully dissociates is no longer reversible, but something that is weak, it can turn back, which is why it only partially dissociates. You can use the word dissociate. You are allowed to use the word ionize. You cannot use the word dissolve, right? Dissolve is solid to liquid, so cannot. Ionize or dissociate is the 2 wording that are accepted in your exam. After we are done contrasting strong versus weak, I want to bring your attention to a H plus versus a 2H plus. We consider this mono. Mono means 1. So if you form 1H plus, you are monobasic. If you form 2H plus, you are dibasic. Can? So monobasic versus dibasic simply addresses how many H plus you produce. That's all for this portion on acid. Let's move on to base. Okay, I think there's an equally important discussion to be had when we talk about base. Now, when we are describing base, I need you to know that base is referring to any metal oxide or metal hydroxide. Now, metal oxide, what do I mean? I wrote down a few examples here. It could be iron oxide, copper oxide. In essence, as long as you pair a metal with an oxygen, it is a base. Or it could be a metal with hydroxide. So FeOH2, copper hydroxide, these are all considered bases. Okay, so there are a lot of bases. You go to your periodic table, you got see how many metals. Everything you pair with an O or OH is automatically a base. So there's a very huge group or a very big umbrella. We call them bases. Now, what exactly does a base do? A base simply neutralizes with acid. All right, so that is the chemical reaction that you need to know. But let me elaborate a bit further. This one is the part I need you all to understand. Base is very big. There's a lot of base. But within these bases, right, there's a very small, very tiny elite group that we call alkaline. And what's so special about this group? What's so special about alkalines? Alkalines are soluble in water. Indirectly, I'm implying that most bases are insoluble. But if you are soluble, you get an elite status. You are known as alkaline. And alkalines are the ones that dissociate in water to produce OH minus ions. Naturally, what I expect you to follow up and ask me is this. Sure, okay, base a lot. Most of them insoluble. Alkaline a little bit soluble. Follow-up question, sure. So which is the ones that are soluble, right? So among all of your metals, which are the ones that actually form alkaline? You can narrow it down to group 1 and some group 2. Some group 2 is specifically calcium and barium. This means that if you're not within this very select group, meaning you are group 13 or you are transition metal, you are just an insoluble base. But if you're in group 1, group 2, you form a soluble base, you can call yourself alkaline. So the acid that we are thinking of that forms H+, the brother is alkaline that forms OH minus. Okay, but acid reacts with both insoluble bases and alkaline equally. It's still neutralization. So what I need you to take away here is to understand the difference between base and alkaline. I make it more chim, you see you can understand. Alkaline is a subset of base. You get it? Because alkaline is a very small group under the family known as bases. All alkalines are bases, but not all bases are alkaline. I repeat one time. All alkaline are base. They are just soluble bases. But not all bases can be considered to be alkaline. Because there are a lot of them, they are insoluble. They do not fit into the elite status of soluble bases known as alkaline. Clear? So you haven't learned this before in school, you learn it here today, right? Alkaline is not exactly the same thing as base. It's a soluble base. I'll move on. In your whole syllabus, the most common alkalines you'll see that are strong in nature is sodium hydroxide and potassium hydroxide. There's actually only one weak alkaline. It's aqueous ammonia. But as long as you're alkaline, you need to recognize you will form OH minus. That is the rule. It's the same as acid, you have to form H+. Otherwise, you're not considered an alkaline or an acid anymore. Strong weak, I'm not going to talk about it again. So moving on. I'll skip this part first, not because it's not important. I teach you all something else, then I come back here. The 3 reactions involving acids are very clear. I expect you all to know this already. Acid plus metal. Can you answer me? What are the products we should get? Salt and hydrogen gas. What's the common mistake we associate with hydrogen? H or H2? H2, okay, promise me to remember this when you form your equation. Second equation is acid plus carbonate. We get 3 products. What are they? Salt, carbon dioxide gas, and water. Lastly, when we do acid plus base, what do we get? We get salt plus water. We also call this neutralization. I expect you all to know these 3 acid reactions well enough. The highlighted parts is for you to fill in should they test you on ionic equations. Now, I'm just going to very briefly talk a bit about ionic equation as you're copying all 3. I'll say what is important for ionic equation is for you to remember anything in aqueous state, you break it down into the ions before you eliminate the spectator ion. If I have the opportunity to later, as we go through the mock paper, I'll show you a sample. Okay, but for now, focus on copying down so that when you use the notes to revise, it is complete. So I'll give you all about a minute here to copy the ionic equations, including my students who are online now. So far, I haven't been getting much questions, but please feel comfortable to just ask questions. I love questions if you do not know. Okay, because it means you're actively thinking and clarifying your doubts. I'm just looking at the amount of crocs in class. Oh, amazing, eh? And everybody buy white color. Is it very easy to get dirty, no? I bought the light brown one. Don't eat me lah, it's my personal taste. Okay? But white does seem nicer. Damn it. Okay, another 20 seconds before I wrap up. If you're a bit slow on copying, just take a photo lah. Alright, it's okay. Then no need so stressed out. You can slowly go and copy later on. Okay, I see a question in the chat. So, for hydroxide is considered as base. Yes, you can consider hydroxide as a base. But take note, when you're hydroxide, it doesn't guarantee you dissolve in water. It depends on who is the metal you're paired with. If you're paired with group 1 or calcium or barium, your hydroxide version will be soluble. That would qualify you as an alkaline. Any other metal with hydroxide is just known as base, and they just undergo neutralization with acid. Okay, next, I'm going to zoom in over here. This is the part whereby I'm going to slow down a little because of how important it is. If you learn 3 acid reactions, most of you actually know that. All right, if you haven't studied, go and study. These 3, most of you will know. But do you all know that there's actually 2 alkaline reactions? The first one, no problem. Everybody recognize neutralization when you add acid with alkaline. The one I am truly worried about, where I put a triple asterisk, is the second equation for alkaline. Usually, this is where you drop off, meaning you do not know this. So I'm going to emphasize on this. I'm going to tell you exactly what is the question that's going to come out for your Sec 3 end of year exam. Okay? If I bet $1 with all of you in this class, right, I think I'll win the bet. Because most of your schools will set this for your EOY exam. Whether it's MCQ or structured, I won't know, but they are likely to test you on it. So let's spend a bit of time to properly talk about the second equation for alkaline. Okay. Now, if you take a look at the second equation for alkaline, the reaction goes like that. You have alkaline, it reacts with an ammonium salt. To be very clear, ammonium is an ion. It is NH4+. A salt means it might be paired together with a NH4Cl, NH4NO3. Doesn't really matter. But your compound itself contains NH4+. If that's the case, there will be a reaction. You actually get 3 products. You will get salt, water, as well as ammonia gas. Now, this reaction is very important as it's one of the few reactions that actually produces ammonia gas. But more importantly, how would the question look like, right? How is this equation itself tested in a form of a question? This is when I like to toggle to my extra slide deck. Let me show you. It's the same one as what you see over here. Okay, never mind. I use this one over here. You remember the previous page I said that you can see this over here? It's talking about the same thing. But I always like to show the version of a question. Okay, so how the question would phrase is this. Why shouldn't we add slick lime, which is technically calcium hydroxide? Why do we not add it together with fertilizers that contain ammonium? The reason is because, as we have learned, they will react with each other. Now, give you some context. Why would farmers add alkaline to the soil? Acid rain, the soil is too acidic, your plants cannot grow well. So farmers like to add alkaline to neutralize the acid. At the same time, they also want to add fertilizer. Why? Because fertilizer introduces the nitrogen into the soil and helps the plant grow better. So you get better yield for your crops. It's okay to add alkaline, it's okay to add fertilizer, but it is not okay to add both of them at the same time. Why? Because your alkaline will end up reacting with your fertilizer. And let's see the aftermath of what happens then. If calcium hydroxide reacts with your ammonium salt, it will form salt, water, and ammonia gas. I need you to recognize that the ammonia gas, which is NH3, it will escape. It will just float away. The nitrogen that was supposed to go into the soil is now floating away. The alkaline that was supposed to react with the acid went to react with the fertilizer instead. So what is the outcome? The farmer did nothing. He ends up with an extremely smelly farm because ammonia is pungent. Okay, so what will the question look like? They will have some version of this phrasing. What you need to know is that what they're testing you on is the equation whereby they say ammonium salt plus alkaline gives you salt plus ammonia gas plus water. They could challenge you to write out the chemical equation as well. But this is based on you knowing the equation of alkaline plus ammonium salt. If you don't even know that triple asterisk equation, you cannot explain nor solve this question. I'm telling you, this one has a very high chance of coming up in your exam. Okay, so what I want you to do here is to recognize this question when it appears, and also going back to your notes, I want you to see how this is being covered in your notes as well. So let me toggle back to your revision kit. So over here, the scenario is you have acidic soil, unsuitable for plants to thrive. So what do? Firstly, you add in fertilizer that contains ammonium because your plants need nitrogen to grow well. You also add in calcium hydroxide to neutralize the acidic soil. Yeah, of course. Okay, but what happens if you add both at the same time? Instead of you neutralizing the acid, you would then react alkaline with the ammonium salt, as you can see over here. Ammonium salt reacts with alkaline to give you salt plus water plus ammonia gas. So the gas released now is no longer able to absorb the nitrogen content because the nitrogen is now in the form of ammonia gas and it bubbles away. Not bubbles, like diffuses away. So this is the exact part in the notes that addresses this. But I find it to be more intriguing when I talk about it in context to the question you're expected to solve. If you have any doubt, just trust me first. Study this properly. It will come out. And when it comes out, you can call me a chem god or whatever. But no, this is just based on data. Because every year, Sec 3 end of year, they test this. Most schools. So if you're going to the exam, you're doing yourself a disservice if you do not know how to do this question. It's either 1 mark in MCQ or 2 marks in structured. Sometimes 3 marks if it forces you to form the chemical equation. So there's no running away from this. O level, it came out about twice in MCQ. In the past 10 years. Okay, if I say 2 means out of the past 10. So must know. Okay. And all right, with that, I'd like to carry on our discussion into the next part. I hope this part I have emphasized it and you guys acknowledge how important it is. Okay, if you cannot copy in time as usual, take a photo. So last 10 seconds before I move on. Okay, I recognize that the pacing is a little bit fast, but I hope you all understand it's because I want to make sure I cover every important part. So I have to move on where I need to move on. Okay, but even I know it's a bit fast, but no choice. Because I need 3 hours. I need to hit all the important parts because you will need them when your exam comes. Okay, for the pH curve itself, right, what I need you all to see over here is how it works. For questions that test you on the pH curve, what I need you to acknowledge is where it starts and where it ends, because that tells you the kind of acid you're using and the kind of alkaline that you're using. So if you start at pH 1, definitely it's a strong acid. If you end at pH 12 or 13, you are using a strong alkaline. So your reaction itself, they will test you, hey, which is my combination of acid alkaline here? You need to select the correct one. In contrast, if it's a weak acid, it will start at pH 3. If it's a weak alkaline, it starts at about pH 11. So you need to know how you consider pH in context to strong and weak acid, strong and weak alkaline. At this very moment, you might not know what I'm talking about. So immediately after this, I'll show you the equivalent of the question. So this concept, how do they test you? Okay, so it's always concept, application, concept, application. You'll never just find me going through content. Because content alone is useless. You cannot solve question. All right, so this is the content. Analysis based on pH to determine the choice of acid and alkaline that was used. How would the question look like? Let me go over to the question now. So this is how a question could look like. So over here, you will see the neutralization curve. You need to study the start point at pH 1. Strong or weak acid? Strong acid. So among my 4 choices, I will eliminate ethanoic acid because it's a weak acid. What are the only 3 strong acids in your syllabus? Nitric acid, HCl, hydrochloric, and sulfuric acid. All right, so over here, which is the strong acid that was used? Nitric acid. Now, where did the curve end off at? pH 9, right? So is it a strong or weak alkaline? Weak alkaline. And what is the only weak alkaline in your syllabus? Aqueous ammonia. Therefore, answer here is D. You all get what I'm saying? So you just analyze the start and the end point, you will be able to solve questions. However, this is not the only question type associated with the neutralization curve. There's one more. And let me elaborate. It means choice of indicator. What do I mean? Take a look at the part I've highlighted in yellow, whereby it's almost like a vertical line. This vertical line indicates the point whereby your acid fully neutralized with your alkaline. You will see a rapid change in pH. Now, typically when we add acid and alkaline and we react them, we cannot determine when it has fully neutralized. So what do? We like to add in an indicator. Because when they fully neutralize, your indicator will change color. So what indicator do you choose? You choose indicator A, B, C, D, or E. How do you know which is an appropriate indicator? It's by looking at your curve. If your indicator changes color within this yellow color range, it is the correct answer. Okay, so your indicator's color change must occur within the yellow color vertical line part. Hypothetically speaking, you need to choose an indicator that changes color between 4 to maybe 10. This one also maybe about 3 to 10. This one here, what should the color change range be? Somewhere from about 7 to 11. So that is the choice of indicator. Once again, I bring you over to an actual question. Then we take a look. All right. So how would the question look like? Follow me through. We start with graph 1 first. Graph 1, are you able to see this is the straight part? Around value agak-agak lah, 4 to 10. So if my color change is to occur between 4 to 10, which indicator here is appropriate? Can I use methyl orange? Cannot, right? Because methyl orange changes color between 3 to 4.5. I need it to change color between 4 to 10. So actually the next 3, whether it's 4 to 6, 6 to 7, 8 to 9.7, actually all 3 can be used as the indicator for graph 1. You get what I mean? You just need to match the color change range with the range that you see on the graph. We bring our discussion to graph 2. Graph 2, what's the range? You take a look over here, where I've highlighted. 8 to 10, right? So which is the appropriate indicator to choose for graph 2? 8 to 10. 8.1 to 9.7 is perfect. So what's your answer? Cresophytolin. All right, I know you all cannot pronounce it, but its answer is B. That's all. Do you need to memorize the color changes? No. Do you need to memorize when the color change? No as well. This information will be provided in the question. What you're required to know is selecting the correct indicator. Clear? So what are the 2 question types that can come out for the neutralization curve? Acid, alkaline, strong, weak. Based on where your vertical line is, which indicator do you choose? That's all. Clear? Okay, concept, application. If not, I'll continue to push on. But I see some questions in the chat, so let me take a look. Thank you so much for those who are sending on the link. It's very helpful. So for those who joined late, the chat will help you out. Okay, now lastly, before I wrap up acid bases, the final concept here is the type of oxides. To be very clear, there's exactly 4 types of oxides. Basic oxides are metal oxide. In case you haven't realized, basic oxide is literally this. Let me write that down, because I'm not confident you guys know this. Remember the base that we started discussing at the start of the chapter? The one that reacts with acid is basic oxide, which is any metal oxide or metal hydroxide. If you're acidic, you're non-metal oxide. Okay, your NO2, SO2, CO2. All of these are considered acidic. There's only strictly 3 amphoteric oxides. We usually remember the term ZAP. Z for zinc, A aluminium, P is Pb. Amphoteric oxides are very unique because they can react with both acid and alkaline. Clear? The last one that is usually the neglected child is the neutral oxide. So neutral oxide, there's actually 3 of them: NO, CO, H2O. NO is neutral. NO2 is acidic. CO is neutral. CO2 is acidic. So don't get confused here. My style of teaching chemistry sometimes a bit more nonsense, but whatever, you guys are sitting through this. So how I remember which are the neutral oxides, right? Tell you a bit of a story. So back when I was in NTU, right, one of the things, I went for my basketball training. Okay, on the way there, right, there was this cute little squirrel trying to drink water because it was a very hot day. So it went to the water cooler and then it keeps like nibbling at the part, you know, the water cooler part, but no water come out. Because obviously you need to press it, right? So why did I tell you this story? I just want you to remember that when the squirrel went to the water cooler, there was no cold water. Huh? What are you talking about? No cold water. Get it? It's a bit nonsense, but if you cannot remember neutral oxide and in your head you see this squirrel trying to drink from the water cooler, it helps you. No cold water, use it. Okay, so my style is like, if there are things I need to memorize, I try to make it easier. Sometimes it's a bit nonsense, but I think it makes it more fun that way. Okay, so neutral oxides, no cold water, 3 of them. I will now move on to salts because after that we can wrap it up and we can take a break before we go to the mock paper. So let me bring your attention back to the handout. Let's talk salts. Okay, for salts, right, instead of just going through with you the salt solubility table, I thought it's important to emphasize to you why it's important. Because if you do not know your salt solubility table, you cannot solve questions. You cannot know what is the correct salt preparation method to be using. But earlier, I already showed you my secret, right? Which is how do we remember things more easily? So follow me through step by step first. You can copy this down later. For soluble versus insoluble, I think most of you know this when we say spa. Right? Imagine you go to a nice spa, you dissolve, you are soluble inside that hot tub. Anything with spa is soluble. And SPA stands for sodium, potassium, ammonium. Any salt that has any of these 3 straight away soluble. Don't even debate. Okay, next thing, all nitrates are also soluble. But if we agree, right, this one is not difficult. The one that's annoying and hard to remember is actually your chloride because there are some exceptions to the rule. So let me run through with you my own way of memorizing this. I'll start with the sulfate first. I like this because sulfate starts with an S, right? S here stands for science. What are the 3 sciences that you take? Bio, Chem, Physics. P, C, B. B stands for bio. Bio is B, B, A, barium. Chemistry is C, right? C is Ca. Physics is P, Pb. So what I'm telling you here is, yes, you could memorize this 3, or you can find an easier way to recall it. So instead of hardcore memorizing, oh, these are my 3 insoluble sulfates. If you cannot remember, go back one step. S, science. What are my 3 sciences? Right? And from there, you can remember what are your 3 insoluble sulfates. You will not remember, no, you will not forget your 3 sciences. So this is in a way foolproof. Even in exam, you panic, you can still remember it. So personally, I'm not a big fan of hardcore memorizing. If it means the squirrel drinking water or science, your 3 sciences, I rather you remember this than memorizing. Clear? Okay, now what about for chloride? Chloride, my own version is this. I link it to spa. You know, like when you go to spa, right, you don't want your hair to drop everywhere. So what do you wear? You wear a shower cap, right? So your hair is all stuck in the shower cap. Cap, C-A-P. Cap, C, chloride. Which are your 2 insoluble chlorides? A-P. A stands for Ag, silver. P, Pb, lead. So for chloride, my own version is like when I go for spa, I wear a shower cap. CAP. So what you need to remember from here is just this. Spa, nitrates. Insoluble one is just your cap, your shower cap, and your 3 sciences. You don't tell me you cannot memorize this. True? Right? It's about how do you make life easier for yourself. So even my current students right now, they follow the same framework and they have no problem recalling it at all. Maybe after some time, if your brain is good, you will automatically recall without this. But what I'm telling you is make life easier for yourself. You don't have to use this exact same terminology as me, but you can find a way to make it easier for yourself. That's all I'm saying. Clear? So now that we have clarified which are soluble, which are insoluble, I want to bring the rest of our discussion to this. How many salt preparation methods are there? 3, right? Come, can anybody help me out? What are the 3 salt preparation methods? Titration, precipitation, and reaction with acid, or I call it acid reaction. What is important is not for you to memorize the procedures. Meaning when I do titration, step 1 to step 11. Screw that. Why? It comes naturally, right? Because it's very logical. What you need to focus on is when I'm preparing a salt, when do I use which method? You don't need to answer me. I'm going to say out a few salt. Okay? If you know the answer, you shut up. If I'm preparing copper sulfate, which is the correct method? If I'm preparing sodium chloride, what's the correct method? If I'm preparing silver chloride, what's the correct method? If it doesn't come naturally yet, it means you haven't mastered this chapter. But I promise you, if you give me 10 minutes, after this 10 minutes, you will be able to tell me the answer. I'll ask you the exact same question after 10 minutes. Can? But you all need to follow me closely. There's only 3 methods. Focus on when to use which method. That is understanding, right? Not memorizing. This is how we approach it. Very simple. If you are preparing an insoluble salt, there's only one method. What's the correct method? Precipitation. As the name suggests, precipitation, what's the base word? Precipitate. And precipitate is insoluble. In other words, if you are trying to prepare a salt that falls under the right-hand side column, whether it's your CAP, your 3 sciences, or any carbonates except for spa, anything that's insoluble should be prepared using precipitation. How does precipitation work? It's actually simpler than it seems. Let's say the example we're going with is lead chloride. Lead chloride is an insoluble salt. Chloride, what do we recall? Shower cap, right? CAP. Chloride, C. What is A, what is P? Silver and lead. Lead chloride is insoluble. So therefore, we should be using precipitation. So how does precipitation work? If I want to form lead chloride, I need to add in 2 things that are soluble. And out of these 2, they must contain the lead that I want, which is Pb2+, and it must contain the Cl- that I want as well. Only then I can form my lead chloride. So let's start with Pb first. I need a soluble version of lead. So what do I add in? Lead nitrate is the smartest choice. Why? Because all nitrates are soluble. So when you do precipitation, whatever you pair with, right, just pair with nitrate. Confirm soluble. So lead nitrate is the first reactant that you pour into the beaker. The second reactant now must contain the chloride. So what do we add in? We add in sodium chloride. Why is that a smart choice? Spa, right? Sodium is Spa, S. So anything with sodium is confirmed soluble. Another popular choice is HCl, because all acids are soluble as well. So when you add in these 2, what happens? The lead and the chloride, they are now floating around in the solution. They see each other, they fall in love, they come together. It forms your precipitate lead chloride. Whatever remaining in the solution is just your Na and NO3. How do I get this salt? I simply do filtration. My residue is my insoluble salt. Done. So what is precipitation? I use it when we are preparing an insoluble salt. I mix soluble plus soluble to get my insoluble salt taken out via filtration. The residue is my insoluble salt. Can I do more examples with you? Sure. But it's the same concept. Every time you're preparing an insoluble salt, we do precipitation. And this is how we do it. The procedure itself, if you run through, is just add this, stir it, filter, residue. Done. You don't tell me you need to memorize the procedures. Because once you understand it, it comes naturally. Are we good with the first method? I rephrase it. When do we use precipitation? When we are preparing insoluble salts. Now, we bring our attention to the other side, which is a little bit more complex. Because here, right, we are preparing soluble salts. But soluble salts, there's two methods. There's titration and there's also acid reaction. So when do I use which method? Very simple. Your VIP status, the one that goes to the spa salon, uses titration. Only spa. You need to be VIP status. SPA, then you use titration. Anybody else, yes, you are soluble, but you don't belong to the spa category, you do acid reaction. I repeat one more time, soluble salts, there's a lot. If you are spa, titration. If you are non-spa, you do acid reaction. Let's run through each of them, one example each. So over here, right, there's further annotation. Let's run through the spa version first, okay, which is potassium chloride. If I want to form potassium chloride, remember this. If my method is titration, titration should be done between an acid and an alkaline. If I want to form potassium chloride, potassium, what is the appropriate alkaline to use? I'll use KOH because I need the potassium. If I want the chloride, what is the appropriate acid to use? HCl. Because when I do so, acid plus alkaline, it gives me two products. What are the two? Salt plus water. So the salt itself is potassium chloride. With my potassium chloride in a water solution, I'll do crystallization to obtain solid version of my salt. That is how titration works. So what am I telling you here? If it's titration, 90% of the time is acid plus alkaline. The only problem here is that when I react acid with alkaline, I have a fixed amount of acid, I add in alkaline. But I don't really know how much alkaline to add. So what do? I add an indicator. So that when the color change, I know, stop. This amount of acid should be with this amount of alkaline. Then I redo my whole experiment again with the same volume, but this time without the indicator. Get it? Because the indicator is an impurity. So the first time you do it is for the color change. So you know how much volume to how much volume. After that, you repeat it again, you do crystallization. You get your spa salt. That's it. So titration is just acid plus alkaline. Strictly for the VIP group known as spa. Now, if you are soluble, but you are not spa, what's your treatment? How do I form you? What's the salt preparation method? The correct way to look at this is that it's simply an acid reaction. Let's recall from the previous chapter, what are your three acid reactions? Acid, metal, acid, carbonate, acid, base. Any of these three can form the salt. Now, what do I mean? We use this example of zinc nitrate here. If I want to form zinc nitrate, I can actually choose how I want to do it. For sure, if you want nitrate, what is the acid you should add? Nitric acid, right? Otherwise, how you get the nitrate? But how do I get the zinc, right? How do I form the salt? You can either react the acid directly with the metal, the base, or even the carbonate. Any of it, regardless of which one you choose, you will still get the zinc nitrate, which is your soluble salt. After you have this zinc nitrate, what do? We do crystallization to get the solid version of this salt. So what am I saying here? The third method is just an acid reaction to produce a soluble salt. The reason why we need to add it in excess is to make sure that all the acid would fully react. So what I do is I spam the metal, the carbonate, or the base to make sure that there's no acid left over in my solution. I can always remove this metal, base, or carbonate by filtering it out. But if I have acid left over in my solution, it's an impurity to the salt. So we always spam the metal, the carbonate, or the base so that there's no acid remaining. Okay, so this is how we prepare a soluble non-spa salt. Are we good? Question? You mean for the final method, is it? You can choose any. You happy can already. So the question is, for the preparation of a soluble non-spa salt, do I react with metal, base, or carbonate? You can choose it. But later I'll teach you something special. But I want to go back to the question I asked 10 minutes ago. Are you all ready? How do I prepare magnesium sulfate? First question, soluble or insoluble? Soluble. Is it SPA? So what is the correct method? Acid reaction. Magnesium sulfate, what acid do I use? Sulfuric acid. And I react it with what? Metal, right? I can react with Mg. I can react with base, MgO. I can even react with magnesium carbonate. I want to form silver chloride. Soluble or insoluble? Insoluble. What's the correct method? Precipitation. I want to form sodium chloride. What's the method? Sodium chloride. VIP, right? SPA, right? We do titration. You get what I mean? It's not about memorizing the procedures. Screw the procedures. You know what? Because once you understand when to use which method, this chapter is unlocked. You don't have to memorize anything here. It all comes automatically. So this is the power of understanding rather than memorizing. So you have been a memorizing one for Chem. Sorry, but it's very hard to do very well. Because what I'm talking is always A1. Like if you want to get A1, you need to understand your concepts so that you're able to apply. So that's why there's so much emphasis on understanding the content. But I give you all one last thing to leave you all with, right? Then we go for our break before we go through the paper. I want to talk about the formation of copper nitrate. Pay attention here. Copper nitrate, soluble or insoluble? Why soluble? Nitrate, right? All nitrates are soluble. Is it SPA? It's not. So what is the correct salt preparation method for copper nitrate? Acid reaction. Acid metal, acid base, acid carbonate. So what I've done over here is I've written down this equation where I reacted the correct acid with the relevant metal to produce my soluble salt. Why is this wrong? We literally just said, right, it's acid reaction. I choose my acid. I choose my metal. Sure, then why you mark me wrong? Anybody? I thought I heard something here. What do y'all say? Share a bit lah. What do y'all think? What thing is unreactive? Copper metal, in case you have forgotten, is unreactive with acid. So is this still the correct method? Yes, but you cannot react it directly with the metal, which means what should you react it with instead? You either do the base or you can do the carbonate. I re-emphasize again, the choice of method here is correct. However, due to the nature of copper, you cannot react the metal directly with the acid, but you can still react it with the base or even the carbonate version. So if this is an MCQ question and they say, oh, I'm going to react to form copper carbonate, select the other reactant. What do you think they will write as option A? They will write copper metal. And so many people will just jump into that and choose that as the answer. Then they all get it wrong. But you need to have the awareness that you need to look out for this scenario. Okay, and specifically is the copper and silver. These are the two that will appear, that will screw you over. Clear? So I'm telling you where you'll make the mistake. Don't make the same mistake. All right. And with that, I think I am happy, which means now I'm able to wrap it up because the next segment we're going to move into is the mock paper. So I'm going to go for a 5-minute break here until 3:40. So for those of you who are online, go and take your break as well. But when you come back, we'll start by going through the paper itself. I will be flashing the MCQ answers so that you guys can mark before the lesson itself. So I'll see all of you at 3:40. For those who are here, feel free to snack up. If you have any questions, I go toilet first, okay? Then when I come back, you'll ask me. Okay, let me settle the things in the chat first. The worksheet with acid bases, you mean the slides that I was showing just now, is it? That one wasn't an official handout. I was just referencing it for a couple of questions. But the good news is that I will be uploading this recording onto YouTube by next week. So if you need to reference back, you can always do so. Okay, so that one was a bit of I a bit greedy lah, so I brought in extra materials. That's why it's not directly in the handout. But you should still be able to find most of it in the revision kit. Okay, I hope that clarifies. I go toilet first.
Oh, bro. Go. Yo. Dapat tujuan. Dapat tujuan. Amen. I adjust a bit only. Anybody is like freezing, because it depends on where you're sitting actually. But I will adjust it a little, okay? But as I always say, don't suffer in silence. So if you go with it, turn on the aircon, turn on the Okay, go grab the snacks that you want. Feel free to eat during class, but you must listen to my class. That's the only criteria. I start. You're done stocking up. Huh? What thing? You grab what you want. I ordered another 7 boxes of red mud snacks coming later on. Cause you guys are monsters, but go and eat. It's fine. You want to guess on average how much do we spend on snacks as like an entire OVERMUGGED company? Think about 3 to 4K
just to restock the snacks at every center. But I think it's fine because it really means that if you guys are eating, you're awake and sometimes you're hungry. Okay, so feel free to snack during class, but let's regroup and refocus because for the remaining part of this lesson, we are purely focusing on going through the mock paper. What I think is that some of you did the paper, but not all of you all completed it as well. Especially for those that probably got the booklet today, you might not have done it. But either way, I want you to listen and to follow through. There will be only a couple of questions I'll be skipping, specifically those that are covering oxidation and reduction. Why? It's because more than half of you are not tested on that for EOY. But because some of you are tested, we sprinkled in a couple of questions for extra practice. Okay? If not, I'll be going through starting from question 1 all the way to question 18. Good news, no need to worry about the answer key because it is provided. It can be found online. Okay, but annotations, that means things that I write, that are extra, that one not in the answer key. So copy down those. Those are more important. Copying the actual answer itself, not so much because it's available. Let's start with question 1. Okay, for question 1 itself, there's only 2 things I need to mention before I'll quickly move on. Hydrogen is less dense than air. Hydrogen is H2, the mass is 2. Air is made out of nitrogen and oxygen, which is way denser. So hydrogen, if it's less dense than air, you use upward delivery. Furthermore, if it's insoluble in water, you can collect it using displacement of water. Therefore, correct answer here is D. This one is a minor typo. So just correct answer here should be D. Shouldn't have any problem here. Sorry, question. Denser or less dense, is it? Okay, fantastic question. I was going to gloss over it, but since the question is asked, I'll go through in detail. Now, in one of the chapters that you might not have learned yet, maintaining air quality, you are told that air is actually a mixture. So air is actually made up, 78% of it is made up of nitrogen, 21% is actually made of oxygen. Nitrogen's mass is 28, oxygen mass is 32. If you actually account for the percentages, as well as the mass itself, as MR of air is approximately 29. So what you'll do is to compare the MR of your gas versus air. H2, right, is 2. 2 is a smaller number than 29, which is why we claim that hydrogen is less dense than air. Let's try a few more as a quick rapid fire example. Let's try CO2. What's the MR of CO2? 44. So is CO2 denser or less dense than air? Denser. Let's try another one. NH3. What is this? Ammonia. You are supposed to know this, right? What's the mass? 17. Denser or less dense? Less dense. So the question is, do you need to memorize? Don't need. Because if you know your point of reference is 29, you will know who is less dense and who is denser. Okay? So you never catch me ever saying memorize, because that's not how it works. Clear? So thanks for asking the question and everybody get to learn from it. But this is how we approach density of air in comparison to gases. Let's move on. For question 2 is just a case of diffusion. If you want the balloon to shrink, you need gas X, which is inside the balloon, to diffuse out faster than gas Y can diffuse in. So you need the gas X to be lighter so that the diffusion is faster as compared to gas Y. So you're just choosing an option that gives you this X, which is MR lower than gas Y. Therefore, answer is A. If you don't understand, you immediately ask already. No need to hesitate. When you ask, everybody can learn as well. Okay, I will move on. Question 3, sorry. Aircon cold, no problem. I off one of the aircon first, okay? Then if anything, you all let me know, I'll turn it on again. And then two, so that's still one again. It's quite a clean jacket if you want. Really? Okay, then you won't wear it. Oh, she's cold. You want the jacket? Okay, so next, question 3, right? Lower melting point. First thing I need you to understand is that sodium chloride is metal, non-metal. Magnesium oxide is also metal with non-metal. So what kind of compound are we talking about here? They are both ionic compounds. After we have established that, the next discussion is this. Ionic compounds, they are both ionic. But why is it that one has a lower melting point than the other? It's based on the ionic bond. Now, when is your ionic bond stronger? It's stronger when your charge of your ions is bigger. So a 2 plus and 2 minus would form a stronger ionic bond than a plus and a minus. Meaning a 3 plus and 2 minus is even stronger, right? So that's aluminum oxide, for example. But the main point I'm driving at is that even though they are all ionic compounds, their ionic bond strength is different. It's based on the charge of your ions. Therefore, why does sodium chloride have a lower melting point? Is because the electrostatic force of attraction is weaker. Because Na is between plus and minus, while Mg is between 2 plus and 2 minus. Okay, so this is comparison between two ionic compounds. Okay, I'll give you another 20 seconds, then I'll move on. Question? Yeah. Okay. Next, for question 4, is either you take a photo or you can draw it out. But the main point here is that when we are doing covalent bonds, right, you need to understand as we look at the dot and cross diagram, we need to acknowledge that not all electrons on the valence shell are necessarily involved in covalent bonding. Now, I want to zoom in on oxygen. Why? Oxygen, which group is it in? You still say so confidently, not 2. Which group is it in? Group 16. What is 2? How many covalent bonds does it need to form? 2. Why? Because oxygen has 6 valence electrons. In order to form a fully filled shell, 6, how do I go to 8? I need to form 2 covalent bonds. So the first covalent bond is formed between the C and the O, as we can see over here. And the other is formed between the O and the H. But do you notice after we get 2 electrons involved in bonding, there is another 4 that are not involved in bonding. Which is why the question is asking, how many valence electrons are not involved in bonding? We take 4 because it's this 4 that we are talking about. If you are damn freaking good, you might not need to draw it up. If not, I recommend you drawing up. Okay, so if you are Chem God level, I see this, oh, I know answer is 4. Right? But this cause why? I've been teaching for 10 years, not fair, man. So for you, I recommend you drawing it out so that you can identify it correctly. It will take a bit of time, but I think it's worth it. Clear? All right, if you have no time to copy this, don't sweat it. Why? You just Google what is the dot and cross diagram for ethanol. You'll get the same thing. Okay, I just drew it out so it's a bit easier to illustrate for you. Next, let's move on to question 5. So which particles are responsible for conduction of electricity in an ionic compound? Remember this, ionic compounds conduct electricity via their mobile ions, whether in molten or aqueous state. Let's further this. Do ionic compounds conduct electricity in solid state? They don't. Why? Because in solid state, your ions are held in fixed position, which is why ionic compounds can only conduct electricity in aqueous or molten state. Clear? Okay, if you want to be even more technical, your mobile ions here act as mobile charge carriers. So this is in the case of a structured question, how you explain how an ionic compound conducts electricity, because your mobile ions act as mobile charge carrier. So those are keywords you need to include. Moving on. Okay, next up over here, we see a good lubricant. Do you all know what is this referring to? Quite obvious, right? Hexagonal layers. What is this? It's our graphite. So what I need you to take away from this question is that within the layer, those that I'm highlighting in blue over here, it is strong covalent bonds. it is near impossible to break the layer up. So within one layer, that layer is very strong. But between one layer and another, when they are stacking on top of one another, that bond or the force of attraction is weak. So the yellow color part is weak, which is why it is easy for me to separate one layer from another. A very common graphite thing that you are already using is pencil lead. So why is it that with just a bit of pressure, when you exert on the paper using friction, you are able to leave a layer of graphite on the paper? It's because between the layers is very weak. So it's very easy for me to leave a layer after another layer after another layer. But to break the covalent bonds within the layer itself, between the hexagonal, cannot. So that's why over here, it's a good lubricant because the layers can slide over one another. Are we clear? Covalent bonds are freaking strong. You don't ever break covalent bonds. If anything, it's the weak intermolecular forces of attraction between the layers. Okay, for question 6, why is it not 4? So over here, right, when we say electrostatic, actually this is a good question. Why is D wrong? It's because electrostatic is strictly used for between a positive charge and a negative charge. So when do we use the term electrostatic? It's largely when you're referring to number 1, ionic compounds, right? Because ionic compounds, you have cation and ion. The other one where we bring in electrostatic is metallic. Between your metal lattice and your sea of delocalized electron. So electrostatic must involve charges. Okay, that's why even though the framing is very similar, it is wrong. Because between the layers here, there are no charge. So we consider it just forces of attraction. But that's a good question, so thanks for asking. Next, question 7, I need everybody's attention because earlier I told you we will see another question for limiting and excess. Remember, we are going all the way back to mole concept earlier. This question itself, if you ever see the phrasing, total volume of gas left, it is implying that the question type here will deal with excess limiting. Based on the equation, you can quite clearly see that there is mole ratio that you will subsequently translate to your volume ratio as well. You all remember the question type I was talking about? So over here, what I've done is I've written down the equation again. So if it's a blank, meaning it's a 1 lah. Okay? We were told that there's 30 cm cube of hydrogen, 30 cm cube of oxygen. Now, if my ratio is 2:1, hydrogen and oxygen, I have equal amount to start with. Which one would I run out of first? Which one got not enough? Hydrogen. Because for every 2 hydrogen, you need 1 oxygen. So if I keep using that same frequency, my hydrogen will run out first. And therefore, my oxygen will be in excess. For those of you who don't get it, imagine right now you're working at McDonald's. Okay, you got 30 bun and you got 30 patty. Bun meaning top and bottom, so that's the bread lah. You need 2 bread to kiap 1 meat, right? So in the same context of 2:1, will you run out of bun first or will you run out of the patty first? The bun, because you use 2:1. So which one here is in excess? The excess is your patty, or in this context, your oxygen. You'll run out of your bread first, because it's 2:1 ratio. If you do the calculation, 2:1, if you use up all of your hydrogen, you'll be left over with 0. But if you use 2:1, 30 cm cube will react with 15 cm cube. Because mole ratio is volume ratio. Which means how much oxygen do you have left in excess? 15 cm cube. Now, when they say volume of gas remaining, usually we should add in the reactant that's in excess with the product that we form, right? So 2, 1, 2, 30, 15 to produce 30. But what do we need to be very careful about when we look at water? You look at the part highlighted in green, what's the main takeaway from this statement? At room temperature and pressure, water is a liquid. So if I ask for volume of gas left, should I add in this 30? No, because water is a liquid at room temperature. So to conclude, the volume of gas remaining is just the 15 cm cube of oxygen in excess. Clear? this one will appear. So you must learn how to master this. Okay, there's a couple more questions that are included in the handout today. Extra practice. Go and look at it. But I'll move on from question 7. Next to question 8. Okay, for question 8 itself, when we see this question, I need you to instantly recognize this is a question on percentage purity. Damn obvious, man, the question right already. So let's rewind a little bit. For a percentage purity question, what is the steps we need to do? The 4 steps and the extra step, 4.5, right? Let's recall the equation or the formula for percentage purity. Is your pure over your impure. Okay, a lot of you are copying. You pause first. Listen to me first. What is the thing that will always happen for a percentage purity question? You will get 2 numbers. Remember, we had this discussion. Which one do we not touch until the final step? The mass of your impure mixture. So you don't use this 1 gram to do your 4 step. This 1 gram is strictly used for the final step in step 4.5. Okay, now if you want to do the corrections, go ahead. I want you to run through the entire process. Step 1, equation. Step 2, calculate mole using this 0.86 gram. Compare mole ratio between what you have found in step 2 with what you actually want to find, which is the silver oxide. Using the equation to find the mole ratio and subsequently solving for the actual mass of your pure silver oxide. Then you plonk it into the formula to get the percentage purity. If you're just blindly copying the steps, there's no point. You need to understand what we are writing and why these steps are in such a sequence. Equation, mole. Mole ratio between what you have found and what you want to find. Step 4, find what you exactly the question is asking for. But there's an additional step 4.5 to get percentage purity. Your EOY exam will definitely have a question type either on this or percentage yield. So both you need to master. But I think what's important for me is not the answer here. 58.7, that value is going to change. But the steps to solve it won't change. So very important for you to get the steps right. Okay, that is your biggest takeaway from today's crash course. Okay, I'll stay on this page for another 30 seconds before I move on, because I don't want to rush through the remaining parts, so I'm saving some time for that as well. All the MR that you see, right, you can just copy down first, but if it's an exam, you will need to flip to your periodic table first, right? Then you get all the MR and do your calculation. It will probably take you a solid about 1.5 to 2 minutes to solve a mole concept question on average, all right? But here, lesser time because we're just copying the answer. Okay, last 10 seconds for those who are copying. If not, you can always take a photo, all right, before we move on. Okay, I hope those who are online are following well as well. All right. If not, let's move on next to question 9. Okay. So for question 9, we are trying to find the molecular formula. Please understand this. At the end of the day, your molecular formula is found using this table. This is your working. There's no other way to write it out. This is supposed to be how you present it. Okay. So what you want to do is with the percentages, how do you go from mass to mole? You will take mass divided by MR. After you get the mole, you can then approximate it and find the mole ratio. So the simplest ratio here is for every 1 carbon, there's 2 hydrogen and 2 nitrogen. There's a CH2N2. But the problem here is this. Even if you add up the total mass of a CH2N2, it only adds up to 42. But the question mentioned that your MR is supposed to be 126. So what this means is that having one set of this is not enough. In fact, you need 3 sets of this to form your actual molecule. That's why everything I times 3, your actual compound is a C3H6N6. Okay, since we were using McDonald's just now, a set is CH2N2, right? It comes with 1 burger, 2 fries, and 2 drinks. That costs $42. But your bill is $126. So how many sets do you order? 3 sets. So how many do you get? You get 3 burgers, 6 drinks, 6 fries. And you get what I mean, right? It's just playing with the numbers. Okay, another 20 seconds, then I'll move on. Okay, let's move on to question 10. Okay, I'll still leave the previous part up there for those who are copying. For question 10, they're asking us for the concentration of the resulting solution. It's actually quite simple because the formula for concentration is mole divided by volume. So what I'm doing in the top part, right, to find mole is to take concentration times volume plus the other hydrochloric acid's concentration times volume. But can anybody articulate for me why did I divide by 1000 for the volume? Your units, right? So you say this, but you are supposed to know, right? Otherwise, you will not get the correct answer. Then I'll finally divide by the total volume. But once again, the total volume, I also need to take care of the units. If you put all of that correctly, you will get the final answer, 2.42. Okay, moving on. Okay, for question 11, this is a discussion about ethanoic acid versus hydrochloric acid. What statement is true? I need you to know that when we are looking at the statements here, we need to be able to identify hydrochloric acid is a strong acid, while ethanoic acid is a weak acid. I'll say this one is fairly straightforward. Okay, so I'm not going to dwell too long on question 11. Next, question 12. For question 12 itself, which does not describe, that means is wrong, does not describe, A is false. Why? Because aqueous ammonia is an alkaline. Sodium hydroxide is an alkaline as well. Alkalines don't react with each other. Alkalines react with acid, they do react with ammonium salt, but they don't react with one another. So statement 1 is false, which means it is the choice here. Can, fair enough. Next, question 13. For question 13, I think this one is worth it to slow down a little to make sure we are on the same page. The saying here is that, okay, if we are preparing a salt and we are reacting acid with a metal, which salt should not be prepared using this method? We see lead-2 chloride. Let me go a few steps here. Lead-2 chloride. Chloride. What was the word that we use? We wear a shower cap, right? CAP, chloride. Which are the 2 chlorides that are insoluble? A and P. A, Ag. P, Pb. Lead chloride is clearly an insoluble salt, which means if we were ever planning to form lead chloride, what should have been the correct method? We should have done precipitation. We shouldn't have done acid with metal. Acid with metal is for a soluble non-sparse. That straight away helps you identify out of the options I see over here, B is out. B's choice of method is wrong. It should not be prepared. But let me explain a little bit further. Should you do it, what's going to happen, right? That's an interesting thought process as well. So if you react lead with hydrochloric acid, you will form lead chloride, which is an insoluble salt. This means in reality, inside your beaker, initially there will be a bit of a reaction. But the moment the insoluble layer of salt starts to form a barrier around your reactive metal, the reaction will stop. And you'll see no more effervescence, no more bubbling. So what am I trying to get at here? You should never ever form an insoluble salt using acid reaction, because this exact scenario will occur. So in other words, if it's insoluble salt, we definitely have to do precipitation. So it's not about the procedures, right? It's about when to use which method, right? We need to identify why lead 2 chloride should not be prepared using this method. This is for question 13. Next, for question 14, straight up, titration is meant to prepare what kind of salts? Spa salt, right? Our VIP. So which salt is not prepared by titration? Magnesium nitrate, right? The other three is SPA. Ma. Magnesium nitrate, what is the correct salt preparation method? Acid plus metal, base, or carbonate. Starting to get it? Salts is not that hard once you know when to use which method. Let's move on. Now, how do I differentiate hydrochloric acid and nitric acid? This has a little bit of relevance to QA, but I can still explain it using acid bases and salts. Why do I say so? Now, what I need you to understand is that the difference between hydrochloric and nitric acid is that hydrochloric acid has Cl minus. Nitric acid is NO3 minus. Why is it that I'm adding in aqueous silver nitrate? It's because I recognize that if I put my soluble silver nitrate with my soluble hydrochloric acid, the Ag and the Cl actually comes together to form an insoluble salt. This is the white precipitate that you observe. So by adding in silver nitrate, I'm able to distinguish which is my hydrochloric acid, as that gives me a white precipitate, versus the nitric acid that gives me no observation. Because all nitrates are soluble, you are not going to get a precipitate. Clear? Now, anybody very opposed if I overrun by 10 minutes? Should be okay, right? I teach you all a little bit more, okay? I go over to the notes. I tell you something extra here. I want to cover very briefly on QA. This page over here. So if you all were at salts, it's just 2 more pages behind. Okay, so here's the thing. The QA segment that I'm focusing on is the test for anions. I want you all to focus specifically on how we test for sulfate and chloride. I start with chloride first. Now, if my solution inside, I suspect that there's chloride, what do I add in to confirm that chloride is there? I will add in silver, or more specifically, a soluble version of silver, silver nitrate. What is the purpose of adding in silver nitrate? If I add in silver nitrate and there was really chloride, what would the silver plus and the Cl minus do? They'll come together to form an insoluble white precipitate. So what am I trying to tell you here? How do I test for the presence of Cl minus? I add Ag plus or silver nitrate. Because if it's really present, they will undergo precipitation to form an insoluble white precipitate. We bring the discussion to sulfate. So if we use a similar thought process, how do I test if a solution contains sulfate? I will want to form an insoluble salt as well, right? Because if it forms, it means sulfate was present. So what do I add into the solution? Which sulfates are insoluble? Which signs? PBC, right? So I add in barium nitrate. Because we expect the barium to come together with the sulfate to form barium sulfate. So a lot of your schools, or a lot of teachers, right, what I don't really like is that when we come to QA, they say memorize QA. QA don't need to memorize, because QA can be understood should your foundation in acid, bases, and salts is strong enough. So what at least for now, minimally I can tell you is, if you're testing for chloride and sulfate, just remember we are just doing precipitation. How do I check if the ion is there? I test, I add in, if precipitate forms, it is present. So actually the test for anion is just precipitation for the Cl and the SO4. Can y'all get it? So I'm building in some understanding into QA. I wish I can go into detail, but I'll focus on going through the mock paper first. But that's why I digress a little, but y'all say don't mind overrunning 10 minutes. Hey, squirrel. Okay, sorry. So question 15, why do we add in silver nitrate? Is to in an attempt to form silver chloride. Next, we carry out a series of experiments to test A, which is incorrect. Answer here should be B. Why do I say so? If you're gonna add in barium chloride, right, we expect the barium and the carbonate, they should come together to form barium carbonate because barium carbonate is insoluble. All carbonates are insoluble except for spark. So option B is incorrect because the observation is not no visible reaction. The observation should have been a white precipitate is formed. So this is a bit more on the QA side of things, but it's still relevant, but I just didn't have time to cover in detail. But it's just precipitation, which is why your chapter in salts is very important. Next, I'll move on to question 17. For question 17, I will also talk a little bit about QA here. But what's more important is this. If I have an aqueous solution and I get a green precipitate, without hesitation, you should know green is Fe2+. So you have already narrowed down your option to being either A or C. This one confirmed is Fe2+. No need to debate. The one that I find a bit of value discussing in detail is the second statement. The aluminium foil and a gas turns red litmus paper blue. Write this down for me. If you ever see aluminium, what you're testing for is for nitrate. Let me elaborate what exactly happened. For nitrate itself, whatever, I'm just going to elaborate more. For nitrate itself, why do we not do precipitation? Sulfate, I do precipitation. Chloride, I do precipitation, right? Then why nitrate, I don't do the same thing? Because all nitrates are soluble, you will never get a precipitate. So the only way to test for your nitrate is this. From NO3, right, the aluminium here helps to turn it into NH4+. For those of you who have already learned, this process is known as reduction. Aluminium here functions as a reducing agent. If you haven't learned, it's okay. You will learn it soon. It's only after I form it into NH4+, how do I then go from NH4+ to ammonia gas? What do I add in? I add in alkaline, usually in the form of sodium hydroxide. So where is this aluminium? You can easily spot it in the question, right? It's over here. Where is this alkaline then? We added aqueous sodium hydroxide and it's currently still in the mixture. So what's the main takeaway? The moment you see aluminium foil being mentioned and you get ammonia gas, you can straight away conclude that nitrate was present. In other words, the test for nitrate requires both alkaline and aluminium. Okay, so the trick here is you see aluminium foil is nitrate usually, provided ammonia gas is produced. Okay, but I think writing this down can help you understand it a bit better. If not, I will not be going through 18, 19, and 20 because more than half of you will not be tested on this for your EOY. But we set this question in case those that are tested, you have the practice necessary. So you can copy down the answer if you are tested for oxidation and reduction. Otherwise, we'll move on to the structured questions already. So next, let's take a look at question 21. Okay, so for question 21, we're going to take a moment to firstly do our corrections. And then after a minute, I'll run through part A specifically, because I think part A is quite important. C part 1, by now, I think C part 1 should be doable already. If you got it wrong previously, after today's class, I hope you understand how you get this white precipitate law. Can anybody just tell me what is this white precipitate? Silver chloride law. Remember your insoluble salt? Right? That's why we add in two things that are soluble to form this insoluble salt. Okay, I'd like to talk a little bit about part A. Part A is important. Part A can be tested in a form of an MCQ as well. It's quite common. Now, what is it that you need to learn from part A? Part A states that there are substances that actually contains both covalent and ionic. This might come as a surprise for some of us because we have always strictly talked about ionic as ionic, covalent as covalent. But it is totally possible for one single compound to have both. Now, how does it work? For example, if we look at AgNO3, Ag is Ag plus, NO3 is NO3 minus. So between the plus and minus, this is an ionic bond. Okay, but within NO3 is a non-metal and non-metal. So inside of NO3, it actually is covalent bonds. So this means in a single compound, it contains both the ionic between your cation and anion, but within your NO3, it contains covalent bonds. All right, the same could be said for magnesium sulfate, Mg2 plus with the SO4 2 minus, ionic. But within SO4, it is covalent. Are we good? So the few common suspects are usually NO3 minus. So if you want to, you can write this down with me. NO3 minus, SO4 2 minus, CO3 2 minus. These are the common few whereby they will contain the covalent that could be attached to an ionic, right? Because they got charge, so I can form ionic quite easily. I can pair with anything else, but within it is covalent. The other one to look out for is NH4 plus, because NH4 plus inside is covalent, but when you add this plus to another like a Cl minus, that is your ionic. So if you see any of those that are written in black, it is likely to contain both ionic and covalent. Okay, I will move on from question 1 next to question 2. Any questions before I move on? Okay, let's take a look at question 2. So over here, what we see is the dot and cross diagram. You are only required to draw the valence shell. However, let this be a good reminder. If you drew ionic dot and cross without the bracket and the charge, you actually do not get the mark. Ionic structure for your dot and cross must show the plus and minus. Another thing I want you all to focus on is, do you notice that we actually show this as a dot? This one over here. This is a dot because this electron originally came from the sodium. Because sodium was a 281, it gave away its outermost electron. So even that has to be drawn accurately. You need to understand at Sec 3 end of year exam, there are not that much topics that have been covered in year 1 so far. So the number of question types that they could set is quite limited. Dot and cross is likely to appear, as is a significant component in chem bonding. Okay, and when it comes down to the keywords, when you're required to explain the difference, you usually need to mention 2 things. I always get all of my students to remember, whenever you describe ionic covalent, why is there a difference in melting boiling point? The first mark that you want to hit is mentioning the structure, and the second point is to mention the bonding. So this is structure, this is bonding. This is structure, this is bonding. Now, there's an argument to be made, right? Because MOE did clarify, you don't have to write the answer word for word, same as answer key, as long as the message is being conveyed across. But as a tutor, I find it important for you to understand that if you use the correct keywords, the message that is brought across is a lot easier and therefore is likely to be correct. So there's a lot of value in terms of knowing what the keywords that you have to include. Even if your sentence structure is trash or your English grammar is lousy, it doesn't matter. You'll still get the mark. Which is why I always highlight the keywords that must go into your answer. All right. For my own students, if I don't see the keywords, even though the messaging is right, I will like to mark them wrong. To train them really to get to a point whereby every single keyword is included. That way, you don't lose sleep, you confirm get the mark. If you find your own phrasing, you funny, right, come up with your own version, you might not get the mark. Okay. Personally, as an educator, I don't really fully appreciate this because it's like forcing you into a box. But unfortunately, in the context of an exam, we treat it more like a game, right? So if there's a correct way to score the mark and to score that point, I will take it because that's strategy. But I would say in terms of the broader context of education, it is good to think outside of the box, but not specifically in an exam setting where you want to score the mark. Okay, so don't get me wrong here in terms of like, oh, I'm supposed to only follow model answer. No, but it's understanding the game we're playing here. Okay, I'll stay on here for another 30 seconds before I move on to part B. Okay, like I said, the answer key is already uploaded. So you don't really need to desperately copy everything word for word, but rather focus a little bit more on my annotations and your key takeaway for each question. You need to learn something from each question. That's the purpose of going through questions. Okay, I'll scroll down a little. So for part B, right, unfortunately, I won't have time for y'all to copy this fully, but the only thing I need you to remember here is this. If I want to differentiate, hey, which is ionic and which is covalent, I should test using electrical conductivity. In short, ionic compounds should be able to conduct electricity in aqueous state, but covalent compounds cannot. So what is the example and the equipment that you will set up? It's just testing for electrical conductivity, whether the light bulb will light up or not. Okay, so for the rest of you, you can actually spend some time to read through. Now, the part highlighted in green over here, a circuit that's being set up using 2 carbon electrodes dipped in the solution, you might not know what I'm talking about because you haven't learned it. This is how a circuit is set up in electrolysis. So let me just show you how it looks like. This is how it actually looks like. So you actually have a battery, or in the question context, you actually put a light bulb. Because if electricity can flow through, your light bulb will light up. So this is your solution over here containing mobile ions that should facilitate your electron flow, and therefore current will be able to go. So that part in green color is just this diagram that you see over here. But personally, I say don't stress, because next year in term 2, you will learn this chapter known as electrochemistry. This diagram will make complete sense by then. Your main takeaway at this point at Sec 3, I would say, is recognizing electrical conductivity for ionic compounds versus covalent. As long as you can take that away, you're good to go. So don't be too stressed out about this part in green. Okay, so I'm not going to give you time to copy here because there's a bit too much. Refer to the answer key available online. Next, this one is worth discussing because this is the breakdown when it comes to QA. Now, there is no correct or fixed method to do QA questions. It's about sprinkling in as much information as you can based on the knowledge you have. So let's take this step by step. I want to first look at, we have solid A reacting with acid, it produces hydrogen gas. My conclusion is this: only metal with acid will give me hydrogen gas. Therefore, solid A is just a metal. Next, this hydrogen gas reacts with copper-2 oxide. Now, while you might not have learned the chapter in reactivity series on extraction of metal, common sense will tell you that if it's copper-2 oxide that I'm reacting with, and I get a pink solid, what is this pink solid? It's just copper metal. Okay, but there's no harm copying this equation down. I'm showing you guys how it goes from copper oxide when you react with hydrogen gas, how you actually get copper. You get what I mean? So this is actually how we get the copper. But solid C here is definitely copper. Next, we see over here we have solution B. When we add in sodium hydroxide, we get a green solid. Now I want you to recall, in QA, when we add in sodium hydroxide, we are testing for cations. And when would I get a green solid? If Fe2 plus was present. So the NaOH here, we are mainly looking at the OH minus coming together with the Fe2 plus to form your insoluble iron hydroxide. This is your green precipitate. Okay, in case you haven't realized, this is just precipitation because soluble plus your soluble ion to give you an insoluble salt. Or in this case, your precipitate, which is your iron hydroxide. So if I take one step back, if this tested for the presence of Fe2 plus, it means my solution must have contained Fe2 plus. Actually, if I go one step back, what is solid A? It's just iron metal. Okay, so that's how we do this flow chart. It doesn't go from top down. You always start with the bottom up actually. Now, this is the most important one I like to emphasize. The moment you see aluminium, come, what are we testing for? Nitrate. Remember we said aluminium? When you see aluminium in QA, straight away testing for nitrate. Did we get the ammonia gas as predicted? Yes. This confirms that the anion present in solution B is nitrate. Furthermore, if you are being very smart here, it makes sense for it to have nitrate. Why? Anybody can tell me why confirm plus chalk should have nitrate? Because you reacted with nitric acid. Right? That's how you introduce the NO3 minus into the solution in the first place. Therefore, these are the answers you should be getting. Okay, so I think it's a lot more important for you to take away the analysis, how you think about it rather than the actual answer itself. Okay, so you can always work backwards to determine what has happened. Now, ionic equations and stuff, you can copy down. If I have time, maybe I'll go through, but I'll focus on completing the rest of the questions first. Anyway, for those of you who are confused, the observation, the reason why it goes from green to reddish brown is because when left exposed to air, Fe2 plus will oxidize to form Fe3 plus. Okay, 30 seconds for those working on your corrections before I move on to the next question. Those online, I hope you are following well as well, okay? For the 40 or so of you who are online, ask me questions if you have any, all right? Okay, I will move on to the next question now. So for question 24, unfortunately, we are skipping purely because this is a redox question, oxidation reduction. So for those of you who are tested, I recommend you still doing your corrections. But for those of you who are not tested, still good to write down, but I'll say don't sweat it, because you haven't been taught, you will not be tested, don't stress. Okay, but I'll stay on this page for 30 seconds for those who need to copy down the correct answer. Okay, but please understand, I cannot go through this because there are other questions that I'd like to focus on. Those are the questions that are definitely tested for all of your EOY exams. Okay, because on the next page, we're going to tackle more concepts together. All right, let's take a look. Okay. Now, for question 25. Now, question 25, just now in MCQ, what did we test you? Percentage purity. So down here, what did we do? We did percentage yield. So when you see a percentage yield question, do you remember it will be step 1, 2, 3, 4 and a 4.5, right? The discussion has always been the same. How many values will you be given in the question? 2 values, right? In this situation, you get the 3 ton, which is mass, and 2 ton of ammonia. Which value do we reserve until the final step? Percentage yield is actual over theoretical. The actual yield, which is how much you produce, the 2 ton of ammonia, you will reserve this and only use it in the final step. Don't touch this 2 ton. Your 4 steps that you're calculating should be using the 3 ton of hydrogen. Step 1, equation provided. Step 2, find mole, right? If you have 3 tons of hydrogen, you remember when we say mass in mole, it should always be the units of gram. So we will convert 3 ton to 3 times 1 million gram. And when we take mass divided by mR, we get number of moles of hydrogen. After step 2, you'll do step 3, which is to compare the mole ratio between hydrogen and ammonia. How do we get this 3 and 2? Is by going back to the equation. For 3 hydrogen, you should form 2 ammonia. Therefore, 3 is to 2. So if this is 150,000, this will be 3 is to 2, right? This will be 1 million. So you should form 1 million mole of ammonia. And only then we go to step 4, which is to take mole times MR to find the actual mass of ammonia I was expecting to get in theory. Theoretically speaking, I react this amount, I should get 17 tons. But in reality, how much did I actually get? I only got 2 tons. And that's how I put them in a fraction to find the actual percentage yield. You can't run away from the 4 steps. All right, which is why the sooner you master it, the better it is for you. Okay, because it's always the same old grind. It's always these 4 steps. Which is why I keep elaborating. Today, if you walk away from class knowing the 4 steps, you have learned something big, right? On top of whatever else I'm teaching you. But this is probably the single most important because you can directly apply it to your EOY and you will immediately be able to solve questions. Okay? Right? So that's all for part A. I'll also briefly show how when aqueous ammonia dissolves in water, it releases OH minus, qualifying it as a weak alkaline. But because it's a weak alkaline, please have the discipline to write it as a reversible arrow, not a single-headed arrow. Because a single-headed arrow is for strong alkaline or strong acids. Okay, and then I'll also review the answer for B part 2. Because I want to get some water. Okay, 1 minute for you to get the time. Yes. Generally, it's okay, but if you ask me to write the dissociation equation, I recommend showing how the equals ammonia dissociated. So this can be first, but if I'm not wrong, your answer is the acceptance. Yeah. Okay, then I'll review the last bit. Okay, part C, I'm not even going to go through just because it's easy. You guys probably are able to calculate the percentage by mass. Shouldn't have any problem here. Okay, if you still have remaining revision sessions to attend, I really recommend trying the mock paper first. So that when we go through, at least you've seen the question before, even though you briefly attempt it, so you have more learning points. But if you haven't done the paper, no stress as well, because you still can learn from the question. Okay, I think it's really worth praising that all of y'all are taking your corrections seriously. I think that is really very good to do so, but never ever just blindly copy, right? Because the answer key we provide, so you don't have to be in a rush to copy. The focus is learning from the question. So the things that you write down must make sense. Otherwise, there is no point. Okay, so corrections do, yes, but do it with thinking. Never just, oh, I see the number, I write down. Then there's no point. Okay, because answer key we provide for that reason. Okay, I believe this is the final part. So let's run through this. So over here, we see that the contamination here is either with ammonium sulfate or with ammonium carbonate. We add in barium chloride to test. Okay, now, the first thing I need you to understand is when you add in barium chloride, you are introducing barium 2+ into the solution. Now, why is this important? The introduction of barium 2+ means it can interact with the SO42- or it can interact with the CO32-. In fact, it could interact with either because both of them will form an insoluble salt, whether it's barium carbonate or barium sulfate. So you get the precipitate form in 5 minutes. For now, we are able to determine, is that the carbonate or is it barium sulfate? However, the big thing that gave it away is actually in step 3. Because once I add nitric acid, you see that suddenly my height of precipitate dropped to 0. What does it mean about the interaction between the acid and the precipitate? What happened to them? They reacted with one another. Which brings me to the last question here. Did my acid react with the carbonate or did it react with the barium sulfate? Acid can only react with 3 things: metal, base, and carbonate. So what was the precipitate that formed? Was it barium carbonate or barium sulfate? It's barium carbonate because it's that very same precipitate that reacts with the acid to completely dissolve. So the conclusion here, the contamination, is it ammonium sulfate or ammonium carbonate? Ammonium carbonate. Clear? Can understand? Okay, then only if you understand it, then when you write down the answer, it will make more sense. Okay, so the question here is a case of making sure you understand that precipitate can form, but only one of those precipitates will react with acid. Okay, I'll stay on here for a solid minute for those who are working on your corrections. So do take your time to finish this up.